Good morning, everyone. Can you listen to me? Please raise your hand. See, the laptop got stuck, sir. It really did stuck 2 times. I need to restart. But everyone there, yes, still some 18 students need to join, 18 to 20 students. Everybody, can you listen to me? Please raise your hand. Yes, everybody. Okay, good. Now see, okay, I will review what we did yesterday. But before we go there, we started duals and duality. So quickly, yes, everyone, I will review yesterday's topics also. But first, I want everyone to immediately come into the picture that, yes, you do this, everybody. Yes, my same question, similar question. I want everyone to try this. Okay, write the dual. Okay, the same question. I will repeat this question. That is this question I asked. That is construct the dual. Construct the dual of the following circuit and verify by writing corresponding mesh nodal equations. Okay. Construct the dual of the following circuit and verify by writing corresponding mesh nodal equations. Okay, na? Yes, everybody. Construct the dual of the following circuit and verify by writing corresponding mesh nodal equations. Quickly, everybody, quickly. I'm giving you 2 minutes. We will review what we did yesterday. Construct the dual of the following circuit and verify by writing corresponding mesh nodal equations. Quick, sir. Yes, see, now I'm going with yes, everyone join now. I'm very happy with the strength. Chalo, everybody, can you listen to me again? Raise your hand. See, sir, really, laptop got struck. Maybe the yesterday setup, it updated, sir. The Windows 10 updated. That was the problem. Chalo, now listen. See, I want to construct the dual of the following circuit and again verify by writing corresponding mesh nodal equations. So what is this chapter? This chapter is only a mathematical modeling chapter with which we can model multi-domain system like in analogous systems in controls like a spring mass damper system, etc. We can model. So I want the dual of the following circuit and also I want to verify by writing equations. Okay, na? First of all, meshes become nodes. How many meshes are there? Mesh 1 become node 1, mesh 2 become node 2, and reference is outside. Okay, reference is outside. Same thing I'm taking here, right side. Okay, node 1, node 2, and reference. Okay, node 1, node 2, reference. Chalo, now, now first always include the external branch of meshes. External branch of meshes. Okay, na? External branch of meshes. Now, with respect to first mesh, this 10 volts and 2 ohms are in series. 10 volts and 2 ohms are in series. So that correspondingly become 10 amperes in parallel to 2 Siemens. Yes or no? Yes, that correspondingly become 10 amperes. Yes, 10 amperes in parallel to 2 Siemens. In parallel to 2 Siemens. 10 amperes in parallel to 2 Siemens. Okay, the direction I will tell you. Like here I am taking clockwise. If I take clockwise, I will get minus 10 volts now. Clockwise, I will get minus 10 volts. So KCL here also I will get minus 10 amperes. Minus 10 amperes means entering the node. See, my notation is current leaving the node, I take positive, current entering the node negative. Here clockwise minus 10 volts. Here clockwise minus 10 volts. Here I need to justify by writing 10 minus 10 amperes. So my notation wise minus 10 amperes means current entering the node. Entering the node like that. Then similarly, now if I go to the second mesh, now listen carefully. A dependent current source is in series to resistance, becomes dependent voltage source in parallel with conductance. Becomes dependent voltage source. Yes, it becomes what, sir? It becomes dependent voltage source. Yes, dependent voltage source. Okay, dependent voltage source in parallel with conductance. In parallel with conductance. Okay, dependent voltage source in parallel with conductance. Okay, this 5Vx become 5Ix. Okay, in parallel with conductance. 4 ohms become 4 Siemens. 4 ohms become 4 Siemens. Okay, now in that regard, everybody, again polarity. See here, when I write mesh equation, I2 is minus 5x na KVL. When I take clockwise, current I2 is minus 5x. Clockwise, current I2 is minus 5x. So V2 should be minus Vx. Current I2 should be minus 5x. So V2 should be minus 5x. Minus 5x. Current I2 should be minus 5x. So V2 should be minus 5x. Okay, na? Like here clockwise, I2 is minus current. There V2 should be minus voltage. That is why with respect to this reference ground, this is minus. But 5 become 5Ix. Then now see now common branch. Now between mesh 1 and mesh 2, there is a 3 ohm resistance that correspondingly become, yes, between mesh 1 and mesh 2 or node 1 and node 2, 3 Siemens conductance. 3 Siemens conductance. Now see this dependent parameter. This voltage Vx across 3 ohms, this voltage Vx across 3 ohms becomes current Ix through 3 Siemens. But how they take the polarity? Now, if upper plate is positive, I1 should dominate I2. Na? Yes, if upper plate is positive, I1 should dominate I2. Then only the resultant current will go down and upper plate is positive. So, if I1 dominates I2, Vx is 3 into I1 minus I2. Na? If Vx is 3 into I1 minus I2, then Ix should be 3 into V1 minus V2. V1 minus V2 means current should go right side. Here Vx plus up means current I1 should dominate I2. So Vx is 3 into I1 minus I2. Then Ix should be 3 into V1 minus V2. V1 minus V2 means V1 should dominate. So current should go from 1 to 2. Okay, take your time. I will write equations. First observe this, everybody. Take your time to write equations, everyone. I will explain again. See, Prajit, don't worry, I will explain again. Sir, explain once again. I did not get it. How you are taking points 1, 2, 3? Please see. No, see, meshes become nodes. See, inside mesh node 1, inside mesh 2 node 2. But apart from those two meshes, there is one reference node you have to take outside. The same topology, like mesh 1 node 1, mesh 2 node 2, and here I wrote the same thing like this. Okay, this is node 1, node 2, node 0. Then first external branches of meshes. Okay, shape can be anything. Again, I told Nasar, circuit theory will never get affected because of shape. Don't worry about the shape. You arrange any way you want. You swap the branches, you swap the elements. As long as they obey KCL, KVL, nothing to worry also. Shape is also not specific. Don't worry. But first external branches in mesh 1. Okay, between mesh 1, yeah, there is an external 10 volts and 2 ohms. 10 volts in series to 2 ohms become 10 amperes in parallel. 2 Siemens. But here KVL clockwise minus 10 volts. Here KCL minus 10 amperes. Then again, second mesh, external branches you go. This 3 is called common branch. First external branch. Dependent current source is in series to resistance, become dependent voltage source in parallel with conductance. Okay, like 5ix, 5ex become 5ix, and 4 ohms become 4 Siemens. Now, how to justify the polarity? See here, clockwise, if I take I2 is minus 5x, I2 is minus 5x, V2 should be minus 5ex. Yeah, I2 is minus 5ex, I2 clockwise is minus 5ix, there V2 should be minus 5ix because a voltage dependent current source dual to, yeah, current dependent voltage source, current dependent voltage source. Okay, so here clockwise I2 is minus 5ex, there V2 is minus 5ix. Okay, na? Then this 3 ohms is a common branch between node 1 node 2 becomes 3 Siemens as a common branch between node 1 node 2. See, this 3 ohms is a common branch between mesh 1 mesh 2 becomes 3 Siemens as a common branch between node 1 node 2. But how to take the polarity two direction? If Vx upper plate is positive, current I1 should dominate I2. Then only this branch polarity will be up positive. Resultant will go down. So Vx is 3 into I1 minus I2. Their Ix is 3 into V1 minus V2. That way it should go right. Now I will check with equations. See equations. First mesh equation. First mesh equation. Everyone watch this. Okay. Minus 10 volts plus 2 I1 plus 3 into I1 minus I2 equal to 0. Okay, minus 10 volts, 2I1 plus 3 into I1 minus I2 is 0. Second equation, okay, correspondingly nodal I will write here. You see what? Nodal equation. Minus 10 amperes, okay, plus 2 V1 because current in conductance is V into G plus 3 into V1 minus V2 equal to 0. That is 2. Okay, next. Now if I go to the second equation, I2 is minus 5 Vx. I2 is minus 5 Vx. Second, there also V2 is minus 5 Ix. Okay, minus 5 Ix. Okay, then third dependent source. Vx is link equation we call. Vx is 3 into I1 minus I2. Then only the polarity will come. Okay, here also Ix is 3 into V1 minus V2. Then only this polarity will come. Pratibha, what is your doubt? Pratibha, what is your doubt? Vinita?
No, sir.
No problem. Then all of you please put down your hand. No problem. In case you doubt also, I will take it out. Don't worry. See, my style, what happens, Nasar, individual doubts, if I go, Nasar, individual doubts, it will take a lot of time, sir, because every student may get a simple doubt. But okay, that is the reason. After class, you ask very slowly. I am very happy that after class, if you ask even 1 hour doubts also. Okay? Chalo. Everybody, see, I wrote mesh equations left side, nodal equations right side. See, sir, ditto, they are same. Ditto, they are called duals. Okay, no problem. So now I will give another AC steady state problem to understand this small chapter. It is not a great chapter, but I need to learn this chapter. Then only we can learn some more things. Okay. So now again the question is, I need you to write the dual of the following circuit. I will take an AC transient problem. So everybody, it is an AC transient problem. I want you to write the dual of this. Chalo, quick, fast try. I'm going to tell. Take care of sheet and try to write. Not so big chapter, sir. AC with transient. Though the switch is closing at t equal 0, but all are AC impedances already defined. And I want you to write the dual. Now everyone see here. See again here also for t greater than 0. How to write now? Listen, sir. For t greater than 0, you will get two meshes. Yes or no? Analysis will start when the switch gets closed. It is an AC transient. So for t greater than 0, switch gets closed. Now this is not a transient chapter, sir. Transient chapter we will do it. But before we go to transient chapter, everybody, yes, before we go to transient chapter, yes, we are all learning such concepts of duality. Okay, na? This is not a transient chapter. Okay, transient chapter will start after resonance and magnetic circuit. Tomorrow we are going to start. Okay, now see here. For t greater than 0, switch gets closed. When switch gets closed, yes, everybody, then become two meshes. So again, meshes become nodes. So first mesh 1, node 1, mesh 2, node 2, and reference. Okay, here also correspondingly, okay, this is mesh 1, node 1, and mesh 2, node 2. Okay, yes, mesh 2, node 2, and there is a reference also. Okay, now everybody, in the first mesh, external branches, there is a voltage source in series to switch closing, in series to inductive reactance. Correspondingly, it becomes what? A current source. Okay, current source in parallel to switch opening, in parallel to capacitive susceptance. Okay, capacitive susceptance. Okay, so inductive reactance become capacitive susceptance. Like this becomes now 10 sine 2t amperes. Here switch gets closed. Here means switch gets opened at equal to. Which gets opened at equal. Then that is J2 ohms means J2 Siemens. Positive reactance, inductance, positive susceptance is capacitance. But how to take the direction now? Listen. Here also when I write KVL clockwise, I am getting negative now. Negative 10 sine to 10 angle 0 I will take. Negative. So here also I should get negative KCL. Negative KCL means here also I will get negative KCL means yes, current should enter. Here also I will get negative KCL. Okay, here also I will get negative KCL. Okay, now? Then similarly, right side you go. Then dependent voltage source in series with resistance. Okay, dependent voltage source in series with resistance correspondingly become dependent current source in parallel with conductance. Dependent current source in parallel with conductance. Okay, this becomes 4 Siemens. Now this becomes 6 Vx volts, 6 Vx amperes. Now again direction. Here KVL clockwise when I write I2. Here KVL clockwise when I write I2. Yes, here KVL clockwise when I write I2. I2, when I'm going clockwise, plus voltage coming now. See KVL here, plus 6 Ix volts will come. Plus 6 Ix volts. It is a dependent voltage source. Plus 6 Ix. So here also I should get plus 6 Vx amperes. Here I am getting plus 6 Ix volts KVL clockwise. So here also I should get plus 6 Vx amperes KCL here. But plus means current should leave, na? Plus means current should leave. Yes, this current is leaving. Okay, here clockwise. Okay, plus 6 Ix volts here, plus 6 Vx amp. Okay, plus means current should leave. Okay, that is the meaning. Okay, now. So now I'm writing this part neatly. This is node 2. Of course, this is node 2. Yeah, this is our node 2. Okay, now read neatly I'm writing. Okay, this is our node 1. Okay, chalo, this is our node 1. Now, sir, now what is that? Now see, between mesh 1, mesh 2, there is a resistance in series to capacitive reactance. So automatically between node 1, node 2, there is a conductance in parallel to inductive susceptance. There is a conductance in parallel to inductive susceptance. Conductance in parallel. Series become parallel, na? Okay, 3 ohms become 3 Siemens, and minus J1 becomes minus J1 Siemens. Here negative reactance is capacitive. Here negative susceptance is inductive. But what about the dependent parameter there? Now listen. See, this current Ix is going down. So Ix is I1 minus I2. See, I took both currents clockwise. Ix will go down when I1 dominate I2. So Ix is I1 minus I2. So automatically their voltage Vx should be V1 minus V2. Yes, this Vx should be V1 minus V2. Because this current is going down, Ix is I1 minus I2. Their voltage Vx should be V1 minus V2. Okay. Here switch closing voltage will come. Here switch opening current will excite the circuit. Like that. Here switch closing will excite the voltage. Their switch opening will excite the current. That is the meaning there. That is the meaning of duality there. Okay, now everybody, is it okay? Yes, please answer this. Okay, chalo. Now, sir, we are coming to an interesting chapter, which is again extension of AC steady state. Okay, extension of AC steady state. Why 10 sin tt will be 10 cos 2t? Why phase shift will come? Function of voltage become function of current. If it is sine, right sine. If it is cos, right cos. Why it will become 10 cos? Who created phase shift there? Anirudh, you are wrong. Direction and polarity should be the way you write. I told yesterday also, direction and polarity is any way you can write. It is only mathematical modeling chapter. It should not be the same direction like what you are writing. Closing switch is dual to opening switch, right, sir? Okay, further doubts I write at the evening. Okay, sorry, afternoon. 6Vx direction. Okay, 6Vx direction. See here KVL clockwise. This is voltage now, sir. Here KVL clockwise, I will get what? KVL clockwise plus 6Ix volts will come. Here KCL also plus 6Ix amperes. According to my notation, plus 6 means current should leave the node. Na? Voltage, clockwise positive voltage. KCL positive current. My notation I'm matching. If you have any different notation, you write accordingly, but equation should come same. Okay, na? That is the meaning. This is only mathematical modeling chapter. Okay, your polarities, my polarity directions can be different, not an issue. Chalo, sir. Now we are going to another extension chapter. Now, sir, today we are going to another two small and interesting chapters, but both are extensions of AC steady state. One is resonance and one is magnetic circuits. Okay, so very interesting. I want everyone to pay some attention here. These are very easy, simple chapters, but lot of mathematics will come. So please pay attention, and it is easy to teach. So I'm going to another big chapter called electrical resonance. Electrical resonance. So this is an extended chapter of AC steady state. Everybody please understand. This is an extension chapter of AC steady state. Okay, this is an extension chapter of AC steady state, and lot of things you should study. Okay, yes, electrical resonance in that first point. Okay, resonance is the frequency response. Okay, resonance is the frequency response of a circuit or network. Okay, resonance is the frequency response of a circuit or network when it is operating at its natural frequency. Okay, that is resonance frequency. Okay, resonance is the frequency response of a circuit or network when it is operating at its natural frequency called resonance frequency. Okay, what is the meaning, sir? Resonance is the frequency response of a circuit or network when it is operating at its natural frequency called resonance frequency. Next point. Under resonance, yes, under resonance, the total supply voltage, okay, the total supply voltage and supply current, okay, the total supply voltage and supply current are in phase, that is phase angle phi equal to 0. Okay, phase angle phi is 0, and circuit operates at unity power factor, UPF. Then under resonance, the nature of the circuit is purely resistive. Okay, the nature of the circuit is purely resistive, and maximum power, which power? Active power. Okay, maximum power is transferred to the entire circuit. Okay, maximum power is transferred to the entire circuit by the source. By the source. I want everyone to read this. This is highly mathematical chapters are, but very interesting. I want everyone to please concentrate here. I want everyone to concentrate here, please. Okay. So resonance is the frequency response of a circuit when it is operating at its natural frequency. That means, sir, there are some unique circuits which have something called as natural frequency. Okay, there are some unique circuits which have something called as natural frequency. And when they operate at that natural frequency called resonance frequency, yes, something interesting happens. But what is the observation under resonance? The total supply voltage and supply current are in phase. Phase angle phi is 0 and circuit operates at unity power factor. Okay, the phase angle phi. Okay, the phase angle phi is 0 and circuit operates at unity power factor. Then under resonance, the nature of the circuit is purely resistive. Then under resonance, the nature of the circuit is purely resistive and maximum power is transferred to entire circuit by the source. Okay, the nature of the circuit is purely resistive and maximum power is transferred to the entire circuit by the source. Okay, now, okay, now these are all observations, sir. Okay, these are all observations what happens under resonance. Okay, now. Okay, now I am further continuing. Resonance can happen. Yes, resonance can happen in such electrical networks. Yes, resonance can happen in such electrical networks when we have two similar but opposite natured energy storage components L and C. Okay, resonance can happen in such electrical networks when we have two similar but opposite natured energy storage components L and C. That means, to undergo resonance, there is a special condition, okay, that we will talk, but L and C should be there together, sir. That is the important thing. Only pure or only RL circuit and or only RC circuit resonance cannot happen. Both L and C should be there. So resonance can happen in such electrical networks when we have two similar but opposite natured energy storage elements L and C. Now these energy storage elements, okay, these energy storage elements, okay, these energy storage elements used in such tuned circuits, okay, tuned circuits. We call this as tuned circuit chapter. Okay, tuned circuit. Why we are tuning frequency? So these energy storage elements, okay, used in such tuned circuits must have very high quality. Okay, must have very high quality, which is defined as, okay, which is defined as okay, quality factor or figure of merit Okay, these energy storage elements used in such tuned circuits must have very high quality, okay, which is defined as quality factor or figure of merit. Okay, now this definition Q factor, yes, Q factor definition is, it is 2 pi into maximum stored energy per cycle of supply. Okay, maximum stored energy per cycle of supply by energy dissipated cycle of supply. Per cycle of supply. Okay, maximum energy stored per cycle of supply by energy dissipated. So this Q factor approximate formula is, I will explain sir everything. This is Q inverse by P in watts. Okay, here I am writing a note. I will explain sir again. Listen carefully. In practical applications, yes, in practical applications, yes, in practical applications to resonance used in passive filter design. Okay, passive filter design. Okay, passive filter design and in analog communication. Okay, analog communication. Okay, based receivers and antennas, Q should be greater than or equal to 5. Okay, there is an index. Q should be greater than or equal to 5. In practical applications to resonance used in passive filter design, analog communication based receivers and antennas, Q should be at least 5, sir. There is a meaning, there is an index for design. Okay, then I am writing a table. Element versus Q factor. I will explain everything, but listen, sir. These are all mathematics, lot of things. Derivations also I will do. Pure register. Now in pure register, you see now, register cannot store energy. Numerator is 0, na? Q factor is given by maximum stored energy per cycle by energy dissipated per cycle. But here, yes, it cannot store. Yes or no? It cannot store. So quality factor is 0. Pure inductor, you see. If you take pure inductor, yes, it can store, but it cannot dissipate. It cannot dissipate. Denominator is 0. Denominator is 0 means quality infinity. And pure capacitor also, it cannot dissipate quality infinity. So pure inductor and pure capacitor are the best elements, but they are not available. Then what about practical coil? Yeah, practical coil with losses. This is omega L by R. Then this series RC, high frequency model. This is 1 by omega RC. And then this is series RLC. Now here, out of all these 6 branches, this branch can undergo resonance because both L and C are there. Na? Now here we define quality factor under resonance, that is 1 by R root L by C. 1 by R root L by C. Okay, 1 by R root L by C. Okay. Then here again element versus quality factor. So I am continuing. Now suppose if I take parallel RL. Parallel RL. Okay, this is R by omega L, parallel RC. This is parallel RC. If I go to parallel RC, this is omega RC, and then if it is a parallel RLC altogether, RLC. Now again, out of these 3 right side branches, the third one, RLC, can undergo resonance, both L and C are there. Then quality factor will be R root C by L. R root C by L. Okay, R root C by L. Okay, R root C by L. Okay. Now I'm writing a note. This bit came in GENCO, sir. GENCO 2015. The combined quality factor. The combined quality factor. Okay, the combined quality factor of. Okay, the combined quality factor of. Okay, practical inductor and practical capacitor. Practical means what? With resistors or with losses. That is the meaning. The combined quality factor of practical inductor capacitor, either in series or in parallel. Okay. Either in series or in parallel is given by, okay, Q total is given by, okay, 1 by QL plus 1 by QC is nothing but QL QC by QL plus QC. Chalo, I will explain everything, sir. Okay. Chalo, see derivations. Yes, derivations are there here. Some things I will do which are necessary for us. Some things you just listen and note down. And however, I am going to share notes every day. So make them a copy and keep it with you. Okay, that will be very important. In fact. Chalo, I want everyone to quickly listen here. See, this is another extended chapter of AC steady state, sir, but highly mathematical. So you have to pay some concentration here. Just relax and listen. Here and there, mathematics, right and answer. Today, if we can complete this resonance and magnetic circuits, sir, tomorrow, wonderful day, we will start transients and very carefully, slowly, I will go. And once transient is over, now, sir, we are almost 95% done, and remaining small topics I will teach. Okay, na? So, yes, my intention is to complete as early as possible, sir, because however, this is Diwali and your BTech college is also a lot of holidays coming. So, you know, full attention on GATE, sir. Because finally to get job or to get good MTech, this is the only gateway. Everyone is saying that, yes, people are jobless, etc., etc. But this will be very important. Okay. So now listen here. Resonance is the frequency response of a circuit or network when it is operating at its natural frequency called resonance frequency. Okay, na? Yes, when it is operating at its natural frequency called resonance frequency. Okay, and what is the meaning of this? That means there is some unique secret frequency. If you can operate, then resonance can happen. But under resonance, what is the observation? Voltage and current are in phase angle 0, and circuit operates at unity power factor. Then under resonance, the nature of the circuit is purely resistive. Yes, under resonance, the nature of the circuit is purely resistive, and maximum power is transferred to the entire circuit by the source. Okay, maximum power is transferred to the entire circuit by the source. Then resonance can happen in such electrical networks. Resonance can happen in such electrical networks when we have two similar but opposite nature energy storage components L and C. Okay. Yes, resonance can happen in such electrical networks when we have two similar but opposite nature energy storage components L and C. These energy storage components used under resonance should have very high quality. Should have what? Very high quality. Very high quality. Okay, which is defined as quality factor or figure of merit. Okay. Then quality factor definition: maximum stored energy by energy dissipated. Q in watts by P in watts. Okay, and then practical designs require how much quality factor? Minimum 5. Now, see, resistor cannot store, so quality factor 0. But inductors and capacitor, pure inductor capacitor cannot dissipate, so denominator 0. Now, why I took this approximate formula? See, in one book called Boylsted, this was given, sir. This approximate formula, that is why approximately I wrote. Why? Because you know, in AC circuit analysis, stored energy is our reactive power. Na? Stored energy concept is reactive power. So Q, energy dissipated is real power. Which component can dissipate? Resistor. Resistor is active power, now watts. So that is very interesting formula which came recently in one book called Boylsted he gave, and it is really helping us, sir. So that is why I'm writing all the formulas in this chapter. Then you see now, yes, here you see derivations I will do, sir. Don't worry about that. But first remember, see, exam style is exam style. If it is IS conventional, there I teach in a different way for conventional, those who qualify prelims. See, those students who qualify IS prelims, na, sir, for them conventional coaching is a different level. Okay, na? But this is what, this is very simple now, listen. So, for a pure inductor, quality infinity, pure capacitor, quality infinity, but RL, RC and RLC, yes, these are the quality factors. But out of these 6 branches, this last branch is important because here only resonance can happen. Quality factor and resonance Q naught I will write. Q naught, that is 1 by R root L by C. This we will derive, sir, don't worry. And here also parallel RL, parallel RC, parallel RLC. Here out of these 3 branches, this branch only can undergo resonance because both L and C are there. Now that is why we call this as quality factor under resonance. Quality factor under resonance. Now these 3 formulas, listen, these 3 formulas are ulta to these 3 formulas. These 3 formulas are ulta to these 3 formulas. That you remember. Okay, now there is a meaning there. Okay, then this is a derivation, big derivation available in good books. What is that? The combined quality factor of a practical inductor and practical capacitor. Means inductor with losses and capacitor with losses, either in series or parallel, is given by this. Like imagine, okay, like you are connecting this and this in series. Let us say the quality factor of this Q1. Let us say the quality factor is this in Q2. Now, if you combine both, that become Q1, Q2 by Q1 plus Q2. Okay, like imagine this and this, you are right. So one should be capacitor, one should be inductor. Like imagine that you are combining these two. Okay, imagine that you are combining these two. Okay, now then what happens? This let us say quality factor Q1, quality factor again you can connect in series or parallel. Again combined quality factor becomes Q1 Q2 by Q1 plus Q2 like that. So very very powerful derivations are. This derivation is available in Teresa, John board, Asta Hussain, but this bit was asked in Genco sir. In Genco there is no time to derive this. You have to remember such formulas. Okay na? So now on this sir, gate question. Now I'm giving very simple gate question. Think and tell. Two practical, okay, two practical coils, two practical coils with internal resistance, two practical coil with internal resistance of R1 comma R2, okay, two practical coil with internal resistance of R1 comma R2 have quality factor of Q1 comma Q2 respectively. Two practical coils with internal resistance of R1 comma R2 have quality factors of Q1 comma Q2 respectively. Two practical coils with internal resistance of R1 comma R2 have quality factors of Q1 comma Q2 respectively. Okay. Now if both these coils are connected, okay, both these coils are connected in series, both these coils are connected in series, then the combined quality factor is dash. Quality factor is dash. Two practical coils with internal resistance of R1 comma R2 have quality factors of Q1 comma Q2 respectively. If both these coils are connected in series, then the combined quality factor is dash. Okay, if both these coils are connected in series, then the combined quality factor is dash. Okay, so two practical coils with internal resistance of R1 comma R2 have quality factors of Q1 comma Q2 respectively. If both these coils are connected in series, then the combined quality factor is dash. Chalo, 1 minute, try something. See, understand practical coils means which will come, sir? You know the list. Practical coil, okay, are connected in series, then the combined quality factor I'm asking. Yes, see, yes, sir. He said two practical coils. See, out of all these things, yes, out of all these things, this is considered as practical coil. Okay. This series RL because resistance is a series model to the coil winding resistance, na, sir. Yes, this series RL. And what is the quality factor omega L by R? Now, how you got this also? How you got this? See, suppose I'm just telling why this formula came. Suppose you assume RMS current here. Now we know quality factor is given by reactive power by real power. Na? Quality factor is given by reactive power. What is the reactive power in inductor? That is I RMS square into XL. Then what is the real power? That is energy. Energy is power into time. Of course, into time I am not writing. And here also energy dissipated per cycle. Okay, energy dissipated per cycle. That is nothing but power into time. So here it is I square R. So if you remove that I square, XL is omega L by R. That's why the quality factor of this coil is omega L by R. Okay, na? The quality factor of this coil is what? Omega L by R. Okay, na? That will come automatically here. Okay. Okay. Now, but he said such coils are in series. Now let us come to this question. Okay. Now let us take coil 1. Okay, coil 1. R1, L1. So Q1 is omega L1 by R1. And coil 2, R2, L2. Quality factor is omega L2 by R. Okay. Now if both are in series, both are in series, I can lump them. See in circuit theory, if both are in series, you can lump them. This becomes R1 plus R2 and this becomes L1 plus L2. Okay. Then the combined quality factor, Then the combined quality factor is omega L by R. Okay, then the combined quality factor is omega L by R. We got the answer. Actually, we got the answer. But let us write in the given terms. What are the given terms? R1, R2, and Q1, Q2. This omega is the operating frequency. L is inductance. That is your notation. But you should write the answer in given terms. So what I will do, see this numerator, what I will do, this omega L1 will be there. I'll multiply and divide with R1. And this omega L2 also, I'll multiply and divide with R. So it is same meaning. But however, denominator I am not touching. See, sir, what I did, denominator is same, but numerator omega L1, I'll multiply and divide with R1, and omega L2, I'll multiply and divide with R2. But clearly speaking, this part becomes what? Quality factor Q1. Yes. And this part becomes what? Quality factor Q2. So final answer, yes, the total quality factor is Q1 R1 plus Q2 R2 by R1 plus R2. Yes, Q1 R1 plus Q2 R2 by R1 plus R2. Okay, na? Q1 R1 plus Q2 R2 by R1 plus R2. Okay, na? That is the meaning there. Okay, that is the meaning. Okay, na? Yes, that is the real meaning here. Okay. So now I am coming to, yes, yes, so many wrote correct, sir. So many wrote, some wrote wrong. Yes, some students wrote correct. Okay, right. Now, sir, I'm coming to the first major topic here called series resonance. So this chapter has two parts, series resonance and parallel resonance. So if you are perfect in series resonance, then parallel resonance is also easy. Duality, we can use duality to study that. So I'm taking this series RLC circuit. See, one student asked, sir, what is tuned circuit? Here, tuning means we are tuning the frequency to adjust it to operate at its natural frequency of the circuit. Tuning, like radio tuning, that is, you are varying capacitor there. But here we are tuning first frequency to adjust to natural frequency. So this is a series RLC, but this is an AC steady state chapter. So this is V phasor, I phasor, R, L, and C. V phasor, I phasor, all elements. Okay. Now here we know, yes, now we know at resonance. Yes, at resonance. Okay. First of all, V and I are in phase. So phase angle phi is 0, unity power factor, and total impedance is equal to resistance. Okay, circuit operates at unity power factor. See, under resonance, V and I are in phase, so phase angle phi is 0. Okay, unity power factor, and total circuit becomes resistive. But we know but we know what is Z. Z is R plus, okay, J into XL minus XC for series RLC. Now we know at resonance frequency, okay, at resonance frequency omega equal to omega naught, okay, net reactance has to be zero. Then only it is purely resistive. Net reactance has to be zero. Net reactance has to be zero. Okay. So for all series natured circuits, please understand, for all series natured circuits, what I will do, equate the reactance to zero. So under resonance, because the nature of circuit is purely resistive, net reactance has to be zero. So I'm equating the net reactance to zero. So if I do that, this XL minus XC should be zero. That implies XL equal to XC. So XL is omega naught L, XC is 1 by omega naught C. That implies omega naught square is equal to 1 by LC. So omega naught is equal to 1 by root LC radians per second. So F naught is 1 by 2 pi root LC hertz. Okay, F naught is 1 by 2 pi root LC hertz. Okay, that omega naught is 1 by root LC radians per second, or F naught is 1 by 2 pi root LC hertz. Okay, that is the meaning there. Okay, that means the natural frequency of the series RLC circuit I derived by equating the net reactance to zero. And if I can tune the supply frequency of this AC source, by using some function generator to this value, that is F naught is 1 by 2 pi root LC, that depends upon LNC value, then this circuit undergo resonance. Okay, there is a meaning there. Now, what are all the observations? Now, graph 1. Okay, first of all, graph 1 is the graph between impedance versus frequency. But what is impedance? We know what is impedance, root of, okay, R square XL omega L minus XC 1 by omega C square. Okay, now let us plot this graph. So graph between impedance versus frequency. Okay, this is a graph between impedance versus frequency. Okay, impedance versus frequency. So this is impedance Z versus frequency. Impedance versus frequency. Okay. Now if you observe impedance versus frequency, see, at zero frequency this is zero, but this is something by zero becomes infinity. See, at zero frequency omega L is zero, but 1 by omega C is infinity. So that means it is at infinity at zero frequency. Similarly, at infinity frequency also, this is infinity, but this is zero. That also is infinity. But only at resonance frequency, net reactance zero, na? Yes, only at resonance, net reactance zero. Impedance is root R square, R only it will become. Okay? Impedance is root R square, that becomes purely R. So that is what I want to argue, that impedance is minimum. That means this curve comes like this. This curve comes like this. Why it is coming like this? Why it is coming like this? Yes, let us observe that. Z is minimum R. Yes, why it is coming like this? Now see here, if you observe carefully, at zero frequency, infinity. At infinity frequency also infinity. Only at resonance frequency, net reactance zero, impedance is minimum, there is resistance. Impedance is minimum, there is resistance. Okay. Now I am going to graph 2. Graph 2, that is how mathematically you have to learn, sir. Graph 2 is net reactance versus frequency. Net reactance versus frequency. Net reactance versus frequency. Okay. So again, if I write here, we know net reactance is, what is net reactance? XL minus XC. XL is omega L minus XC 1 by omega C. Okay, this is the net reactance. Now this graph, if I plot, yes, everybody now think about this graph. Okay, frequency, positive reactance, zero, negative reactance. Okay, now see, if you first plot only omega L curve, okay, it is like y equal to mx. Now x-axis is frequency, like y equal to mx. So this will be only omega L curve. Okay, this will be only omega L curve. But what is this? Minus 1 by omega C curve. Minus 1 by omega C curve. 1 by omega c will be like this. Minus 1 by omega c will be like this. Minus 1 by omega c will be like this. Okay. Minus 1 by omega c will be like this. Now there is one frequency. Yes, there is one frequency called resonance frequency where plus x is equal to minus x. Okay, that is the problem. Okay, there is a frequency called omega equal to omega naught where positive reactance is equal to negative reactance. Okay, positive reactance value is equal to negative reactance value in magnitude. That is XL equal to Xina, both are equal. Then X net becomes 0. That is the meaning. X net becomes 0. Okay, X net becomes 0. I only want to show that they are equal. Okay, X net becomes 0. Then the resultant graph will be what? Yes, combination of these two will be like this. This is X net graph. X net. Why? See, only omega L curve minus 1 by omega C. Combination of these two. Now see, at omega equal to omega naught, this total reactance is 0. Okay, at omega equal to omega naught, this magnitude equal net reactance 0. But for any frequency less than resonance frequency, from there, this is less positive, more negative. So negative reactance will do. And for frequency greater than resonance frequency, this is more positive, less negative, positive. But what is the meaning? Now at this point where omega equal to omega naught, net reactance 0 means it is purely resistive. That is unity power factor. Okay, correspondingly if I write here also, that means yes, correspondingly if I write here also, at resonance frequency, it is purely resistive nature. Then for frequency less than resonance frequency, net reactance negative. For frequency less than resonance frequency, net reactance, yellow curve is negative. Net reactance negative means it is what? Circuit, RC circuit. RC circuit means leading power factor. This is leading power factor. So this is RC circuit. That means this zone is working like RC circuit. Okay. Then for frequency greater than resonance frequency, net reactance is positive. Net reactance is positive means it is acting like an RL. RL means lagging power factor. Lagging power factor means this is what circuit? RL circuit. So now read both the graphs together, sir. You will understand. Now conclude understand both the graphs together, then you will understand. See, this yellow curve is a function of impedance versus frequency. Here also this yellow curve is a function of this net reactance versus frequency. Okay. Here at zero frequency, infinite impedance, infinite frequency also infinite impedance. Only at resonance frequency, impedance is minimum, which is resistance. That is why curve comes like this. Here, XL like y equal to mx, like omega L curve will be this straight line. Minus 1 by omega C will be like this. Combination of these two will be the yellow line. At resonance, unity power factor, that is purely resistive. Less than resonance frequency, negative reactance. RC circuit, leading power factor. And for frequency greater than resonance frequency, yes, reactance is positive. RL circuit, lagging power factor. Okay, that is the meaning. That means by varying frequency, all these adjustments are coming. Everyone should understand. We are varying frequency to and getting all these things. So now graph 3. Yes, graph 3. Graph 3 is current versus frequency. Okay, current versus. But what is current? Okay, I is V by Z. V supply by Z. There is nothing but V supply by Z. So if I go to Z, that is root of R square plus XL omega L minus XC 1 by omega C square. Okay. This graph is current versus frequency. Current versus frequency. Okay. Now if you observe current versus frequency graph, yes, if you observe current versus frequency graph, okay, if you observe current versus frequency graph, okay. Now if you observe here, yes, if you observe here, this graph will come like this. Okay, now here, why this comes ulta? See here again, at zero frequency, this is again infinity. Something by infinity, zero will come. At infinity frequency also, this is something by infinity, again zero will come. But only at resonance frequency, this is net reactance is zero, impedance is minimum, so current is maximum. So that is what happens, that at resonance frequency omega naught, okay, this at resonance frequency omega naught, okay, current is maximum, which is I naught. phi naught, which I will tell you. And I will draw another curve like this. Now I will mention that this is for low resistance, high quality. High quality. This is for high resistance but low quality. High resistance but low quality. Okay. Yes, please observe the difference. So if quality factor is high, means minimum losses. Minimum losses means resistance is minimum. See, in this circuit, no one will specifically put resistance. In the circuit, no one will specifically put resistance, but actually resistance is modeling the losses of the system. Please understand. In the circuit, actually no one is putting resistance, but actually resistance is modeling the losses of the system. So in that regard, yes, low resistance means low losses, high quality. Okay, na? And high resistance means yes, high losses, low quality. There is a meaning there. Okay, na? That is what you have to understand. Okay, in the equation only, sir, you observe, you put more resistance, blunt curve will come. Small resistance, steep curve will come. That is the meaning there. Okay, na? Now let us understand phasor diagrams. Phasor diagram. Okay, for different cases. Case one. If omega less than omega naught. Okay, then impedance is R minus jx net. Yes or no? Just now we observed. See, just now we observed that frequency less than resonance frequency net reactance is negative. Na? Net reactance negative means it is acting like RC circuit. RC circuit. In RC circuit, I lead V by phi. By phi, phase angle phi. Okay, less than 90. It is understood. It is a very, very good one. So it is leading power factor. Leading power factor. Leading power factor. Okay, leading power factor. Now with respect to voltage, yes, with respect to voltage, current leads. So phase angle is going this way. With respect to voltage, current is leading, means anti-clock. So phase angle is positive. Phase angle is positive. Okay, I always compare everything with voltage. Then again, case 2. If omega equal to omega naught, impedance is resistance. Then purely resistive. I in phase with V and phase angle phi is 0, which is unity power factor. So that means with respect to voltage, yes, with respect to voltage, current is also in phase. So automatically here phi is 0. Okay, phi is 0. Case 3, if omega greater than omega naught, then Z is R plus Jx net. Okay, R plus, because for frequency greater than resonance frequency net reactance positive now. Yes, R plus Jx net. Now this is like RL circuit. Now in RL circuit, I lags V by phi. Okay. Yes, phase angle. Okay, of course. Phase angle or impedance angle we got. Yes, it is leading. So of course less than 90 is lagging part. Lagging, sir. Let me correct it. Lagging part. Because sir, for frequency greater than resonance frequency, net reactance is positive. Positive means inductive RL. So for frequency greater than resonance frequency, net reactance positive RL circuit. RL circuit means current lags voltage by an impedance angle, lagging part. So here again with respect to voltage, yes, here again with respect to voltage, current lags, yes, okay, current lags. So phase angle phi is negative. Phase angle phi is negative. Okay, phase angle phi is negative. Okay, so as I vary the frequency from 0 to infinity, see, omega less than omega naught, omega equal to omega naught, omega greater. As I vary the frequency from 0 to infinity, phase angle is going from negative 90 to 0 to positive 90. or positive. Yeah, here I took voltage as reference. Huh? Yes, here I took voltage as reference. Like positive 90 to 0 to negative 90 it will go. So now if I combine all these things, yes, graph 4 will come. So graph 4 is phase angle versus frequency. Phase angle versus frequency. So if I plot this graph, phase angle versus frequency, plus 90 is one limit, minus 90 degrees is another limit. So here you observe, as I increase the frequency from 0 to infinity, positive to negative will come. Okay, that means this will go from positive to negative like this. Positive to negative. Like this. Okay, now at this is at omega equal to omega naught, zero phase angle. So this is unity power factor. This is positive leading power factor. This is lagging power. Leading power factor, lagging power. Okay, leading power factor and lagging power. Okay, now that's the meaning here. Okay, this is called phase angle versus frequency graph. Okay, this is called phase angle versus frequency graph. Okay, now interesting, something very interesting. Complete phasor diagram. Complete phasor diagram. Phasor diagram under resonance. Under resonance condition. So this is a series RLC circuit and I want complete. Complete phasor diagram is what? See, these phasor diagrams are phasor diagram only between total voltage, total current. That means supply voltage, supply current. Here complete phasor diagram means all parameters. So I am taking the same series RLC. Okay, same series RLC. Overall voltage, overall current. Okay, RLC. Okay, RLC. And overall VR, overall BL, overall VC. So complete phasor diagram under resonance. Yes, complete phasor diagram under resonance. Everyone please understand this complete phasor diagram under resonance. Okay. Now all the parameters together I am writing. Now here, yes, if I am writing complete phasor diagram, better I take current as reference. Okay, I will write current as reference. Okay, current as reference. But we know that at resonance, yes, we know that at resonance, first of all, XL equal to XC. Okay, in series RLC, XL equal to XC. Current is equal and reactance equal. Now listen, if current is equal and reactance equal, yes, if current is equal and reactance is also equal, okay, then voltages also must be equal. That means magnitude of VL equal to magnitude of VC. Magnitude of VL equal to magnitude of VC. Yes, please understand. Okay, magnitude of VL equal to magnitude of VC. So in that regard, yes, with respect to current, yes, VR is in phase. Okay, VR is in phase. Okay. What about VL? VL will lead I. Chalo, VL will lead I by 90. Okay, VL will lead I by 90. What about VC? VC will lag I by 90. VC will lag I by 90. Okay, now these two are equal. Equal in magnitude but opposite in phase. Equal in magnitude but opposite in phase. Okay, with respect to current, VR is in phase. VL will lead I. VC will lag I. Okay. Now, if you combine phasor diagram, phasor sum of VR plus VL plus VC, see VL and VC are two equal opposite forces. Yes, why? Because their reactants are equal under resonance. These two are equal opposite forces. Net cancel. So VR itself is V. Yes, VR itself is V, and total phase angle is 0. So now the conclusion is here: V is VR. phi is 0 and power factor is 1. Okay, yes, V is VR, phi is 0 and power factor is 1. Okay, V is VR, phi is 0 and power factor is 1. Please understand, power factor is 1, unity power factor. Okay, that is the meaning there. Okay, unity power factor. Now some important observations. Okay, now everybody should understand this. Now you tell me that under series resonance conduction, this pure LC segment acts like dash. Everyone think and tell. See, under series resonance condition, how this pure LC segment together, because net reactance is 0, that means pure LC together acts like short circuit. Yes or no? Pure LC segment acts like short circuit. Okay, then you see total supply voltage is appearing only across resistor. Pure LC segment acts like short circuit. Yes, no doubt. Yes, pure LC segment acts like short circuit and total supply voltage will appear across resistor only. Total applied voltage will appear across resistor only. Yes, total supply voltage will appear across resistor only. Yes or no? When total supply voltage appear across resistor only, yes, please understand. When total supply voltage appear across resistor, then how LNC will work? LNC will work by exchanging the energy. Now this topic is very, very interesting, sir. See now, what I'm trying to say is, just very, very interesting. Listen to this, okay? I'm writing very important point. Under series resonance condition, okay? Series resonance condition. Yes, under series resonance condition, okay? The pure LC segment, of circuit, okay, the pure LC segment of circuit acts like short circuit. Acts like what? Short circuit. It's like short circuit. Okay, under series resonance condition, the pure LC segment of the circuit acts like short circuit. Okay, the pure LC segment of circuit acts like short circuit. Okay, and the source, yes, and the source supplies energy only to resistor. Okay, yes, source supply energy only to resistor. That is why you see total supply voltage appears across resistor only. However, now this is interesting. However, L and C components, yes, L and C components work together. L and C components work together by exchanging okay, the electromagnetic energy and electrostatic energies, energy between them in an oscillatory phenomena. Oscillatory phenomena. Okay. Under series resonance circuit, the pure LNC segment of circuit acts like short circuit. Yes, under series resonance circuit, the pure LNC segment of the circuit acts like short circuit. And the source supply energy only to resistor. However, LNC components work together by exchanging the energy as oscillatory phenomena. Now I will explain, sir. Very interesting. See, what I want to say, see, now with phasor diagram we put that under resonance, this VL equal to VC in magnitude but opposite in phase. So they phase cancel and net voltage across them is 0. See, net voltage across LNC 0 means it is acting like short circuit. It is acting like short circuit. Net voltage across them is 0 means LNC together is acting like short circuit. Then total supply voltage appears across resistor only. So source is supplying energy only to resistor. That is true. Then how LNC are working? To work LNC also they require magnetic energy and static energy, sir. But source is supplying energy to resistor only. But how they are working? They are working by exchanging the magnetic and static energies between them as an oscillatory phenomena. But when this energy would have come initially during transient state or during tuning. See, during transient state or during tuning, na sir. During transient state or during tuning, that energy would have come, yes, during transient state or during tuning, that energy would have come to them. Yes, that energy would have come to them. Okay, na? That energy would have come to them, and that they are, yes, and that they are what they are doing exchanging. Now see this. I will explain with phasor diagram. Now, if I project the phasors, watch this carefully. If I project the phasors, okay. Now current will start here. Okay, current will start here. One cycle I am taking. This is current. Okay. Voltage across resistor is in phase. This voltage across resistor is in phase. Or supply voltage or resistor voltage is same here. Supply voltage or resistor voltage is same here. This green itself is V, which is also equal to VR. But inductor, first if I go with inductor, yes, inductor, it will start here. Okay, voltage will lead current by 90. Okay, voltage will lead current by 90. This is inductor voltage, VL. Okay, inductor voltage. Where is capacitor voltage? Now capacitor voltage, if you observe, yes, it will start here. Okay, it will go this way. Capacitor will go this way. Capacitor voltage. Okay, capacitor voltage will go this way. Okay, now this is what 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Okay, now let us observe what is happening here. Let us clearly observe what is happening. Let us plot. See, I'm plotting both. That is energy of inductor versus energy of capacitor. This is like at 0 degrees. This is at 90 degrees. Okay, like that. At 0 degrees, I will plot. Okay, I will just estimate the value. At 90 degrees, how much it will happen? Okay, and 180 degrees, what will happen? Okay, this is 90. This is 180. This is 270. And this is 360. Like that. Okay. So now listen, sir. One is energy in inductor, one is energy in capacitor. This is energy in capacitor. This is energy in inductor. Watch this, please. Just observe. See, what I'm trying to argue is, all these phasors, na, sir, all these phasors I am rotating together. Please understand the meaning here. All these phasors, if I rotate together, this will come. White line is current line, current phasor. Green line is total voltage or resistor voltage, both are same. And yellow line is inductor voltage, pink line is capacitor voltage. Now, if you observe carefully, everybody, if you observe carefully, see now, at 0 degrees, half Li square is 0, but half CV square is maximum. For inductor, C, state variable inductor current, and for capacitor, C, state variable capacitor voltage. For inductor, C, state variable inductor current, and for capacitor, C, state variable capacitor voltage. Okay, so in that regard, yes, in that regard, at 0 degrees, half Li square is 0, but half CV square is maximum. So this is maximum, but this is 0. Yes or no? Yes. At 0 degrees, half Li square is 0, but half CV square is maximum. Negative, but maximum. At now, when it comes to 90 degrees, half Li square is maximum, but half CV square becomes 0 because voltage across capacitor pink line becomes 0. 0. That means from 0 to 90 degrees, who is giving energy to whom? Capacitor is giving energy to. Yes, capacitor is giving energy to inductor. That means the stored static energy becomes magnetic energy. At 180 degrees, what is happening? Half Li square is 0, but half CV square is maximum. So half Li square is 0, but half CV square is maximum. Again, what is happening? Inductor will give back energy to capacitor. Then again at 270 degrees, half Li square is maximum because negative, but maximum. Half Li square is maximum, but half CV square is 0. Half CV square is 0. Then again at 360 for one full cycle, half Li square is 0, but half CV square is maximum. So this is one cycle. So in one cycle, what is happening? Capacitor will store and release energy to inductor. Inductor stores and release energy to capacitor. Capacitor will store and release energy to inductor. Like that it goes. So here two cycles are happening. See, one cycle, two cycle. So in one cycle of supply, 2 times the energy is oscillate. This was the bit given in gate, sir. How interesting gate question. See. How interesting gate question. See. Okay, the frequency of energy oscillations, the frequency of energy oscillations between L and C, okay, under resonance, okay, is dash. So what is the answer? Answer is 2f0, that is nothing but 2 omega naught, because already this circuit is operating at resonance frequency. Okay, now, but For one cycle of this resonance frequency or one cycle of supply, which is at resonance, two cycles of energy oscillation. Capacitor to inductor, inductor to capacitor, one cycle. Again, capacitor to inductor, inductor to capacitor, second. The frequency of energy oscillations between LC and resonance is 2f naught or 2 omega naught. Okay, 2f naught or 2 omega naught. That is very, very interesting. Okay, this is what you have to understand. Okay, now some I will give break in few minutes of this is an okay. Now see here. Now this is another important note you have to remember, that variation of voltages across passive elements, okay, variation of voltages across passive elements with change in supply frequency, okay, variation of voltages across passive elements with change in supply frequency, okay. Yes, now if you observe that, okay, I will show this side. This is V or Vs supply and talking. Okay. Now, if you take this series RLC, if you take this series RLC, yes, if you take this series RLC, this is V or Vs, this is R, this is L, and this is C. Suppose you put voltmeters here. Okay, if you take 3 voltmeters and put here. Now at zero frequency, inductor open, capacitor open, inductor short. Now at zero frequency, DC, like DC, inductor short but capacitor open. So inductor short, capacitor open. So full supply voltage will appear across capacitor. Yes or no? Full supply voltage will appear across capacitor. And capacitor voltage will go like this. Capacitor voltage will go like this. Okay, then at infinity frequency, capacitor short, inductor open. At infinity frequency, inductor open means full supply voltage will appear across inductor at infinity frequency. Then inductor, yes, inductor figure will go like this. Inductor voltage. Okay, so this is capacitor voltage, this is inductor voltage. And one thing we know under resonance, maximum voltage appears across resistor. Now we already know that. Okay, so yes, that means if you observe here, this is resonance frequency. Okay, otherwise here, let me use frequency F. Sorry, easy to remember. F in hertz I will use. This is F naught I will. Okay, this is F naught I will. Resonance frequency. So now how register will look, how register frequency will look, register frequency, how it will look. Yes, if you observe register frequency or register plot, it will come like this. This red color is register voltage. This red color is register voltage. Now there is some frequency where I will explain, sir. This I will explain again. This is F1 or FC. This is FL. I will explain, everybody listen. Yes, I will explain neatly. Everyone listen. These are all observations, sir. Either you have to do in the laboratory to get this. Very interesting, which I will tell you. Just observe this. I am going to explain now. Yes, we'll take a break. Everybody, take a break. Come back by 9:40. Everybody, take a break. Come back by 9:40. Can you listen to me? Raise your hand. Everybody can listen to me. Raise your hand. I will take up doubts. Yes, yes, it is break. No class. No, 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 sir. State variable, I told na sir, in fourth chapter inductor capacitor, I told na state variable is an parameter which will decide the state of an element. In inductor, it is current, and in capacitor, voltage across it. State variable is inductor current and capacitor voltage only, because that will tell the state of this element when changes happen, which I told you in chapter 4 very clearly. Okay, we'll continue after the break, 9:40. Come back by 9:40. Yes, everybody, welcome back. Are you there? Please raise your hand. It's 9:41 exactly in my clock. Okay, chalo sir. Now listen. See, this graph is the graph between the voltage across capacitor. Okay, this voltage across capacitor. Okay, voltage across inductor. Okay, and voltage across resistor. Okay, now voltage across resistor. Okay, by varying what? By varying the source frequency. By varying the source frequency. Now see at zero frequency, like DC zero frequency, capacitor open, inductor short now. So full supply voltage will appear across capacitor. That is why this is Vs, which is also V. Okay, then at infinity frequency, what happens? At infinity frequency, inductor open, capacitor short. Inductor open, capacitor short. So full supply voltage will appear across inductor. So this full supply voltage will appear across inductor at infinity frequency. At resonance, F naught equal to F is equal to F naught. You know already from phasor diagram we have derived that. Yes, total supply voltage will appear across resistor only. Okay, total supply voltage will appear across resistor only. And that is this. Okay, so yeah, at the same time at zero frequency, capacitor voltage is V, but inductor voltage is zero because no current is flowing. That is why inductor voltage will be zero. At infinity frequency, capacitor open, inductor short. Okay, full supply voltage will appear across inductor, but again no current, no voltage across capacitor, zero. Like that, you have to understand these things, sir. Okay, na? So now, what is the reason we are discussing? These are two important frequencies. See, there are two important frequencies. One is called FC and one is called FL. Okay, there are two important frequencies. One is called FC and one is called FL. FC is the critical frequency where voltage across capacitor is maximum, and FL is one critical frequency across inductor where voltage across inductor is maximum. Where voltage across inductor is maximum. Okay, na? Where voltage across inductor is maximum. Yes. Now, these questions were asked in GATE, sir. This critical frequency FC where voltage across capacitor is maximum. This critical frequency FL where voltage across inductor is maximum. Okay, na? Okay. Now, Navdeep, you understood, Navdeep? Navdeep, you understood? Can you raise your hand, Navdeep? Okay, so that is all. By varying the supply frequency, we get these waveforms. Okay, the graphs actually, they are graphs, not waveform. They are the graph of voltage across resistor, inductor, capacitor. So now, actually, there is derivations. The derivations are for IES conventional, but what are they saying nowadays, and what are they saying? So the first point here is the frequency at which okay, the frequency at which okay, the frequency at which maximum voltage appears across capacitor. The frequency at which max voltage appears across capacitor is. For that, we need to first derive. Yes, we need to derive dVc by d omega equal to 0. dVc by d omega equal to 0. And you will get that value as, yes, 1 by 2 pi root 1 by LC minus R square by 2L square hertz. Now, in that, if I take root LC here, this is 1 minus, okay, into LC by LC, okay, and that is R square C by 2L. That is nothing but F naught into root 1 minus R square C by 2L hertz. Okay, that is a thing. Okay, so this derivation I'm not doing, sir. It is a big derivation. Anyone want, I can share my notes. Okay, don't worry. But this bit was asked. See, in GATE also such things you have to mathematically, sir. That day you do derivation, it will take 5 minutes there only. Then the frequency at which, okay, the frequency at which maximum voltage, yes, maximum voltage appears across inductor is dash. For that, we need to actually derive dVL by d omega equal to 0. dVL by d omega equal to 0. Okay, dVL by d omega equal to 0. That will be FL equal to, okay, we get FL equal to 1 by 2 pi root LC minus R square C square by 2. If you take that root LC common, 1 minus R square C by 2L. So you will get this finally as F naught by root of 1 minus R square C by 2L. Okay. So please understand this. So the frequency at which maximum voltage appears across capacitor and the frequency at which maximum voltage appears across inductor. Okay, these are the two things. Okay, these are the two things. Okay. So that frequencies are these two frequencies. Okay, the derivations you don't do, but remember this, sir. Yes, this was asked in gate. Okay, na? Yes, in gate it was asked. Now I'm extending further. Yes, I'm extending further from circuit. That is series RLC circuit. What you can observe is I is V by Z. That is V by root of R square XL minus XC square at omega equal to omega naught. Net reactance is 0. At omega equal to omega naught, net reactance is 0. Then what happens? This I is root of R square plus 0 square. I is V by R. Okay, and this is, yes, this is maximum. So this is maximum. That I will write it as I naught is V by R. Okay, I naught is V by R. That is why you know current versus frequency graph we already discussed now. Yes, current versus frequency graph we already discussed. You see there? See, current versus frequency graph. Under resonance frequency, current is maximum now, and that value is V by R only. Yes or no? That value is same V by R only we got. That is the same meaning we got. So I will say, so power transferred, which power I am talking? Real power. So power transferred to circuit is also maximum. Is also okay, that is P naught, which is I naught square into R. That is V square by R. V square by R. Okay, that is also maximum. Okay, now another observation that at omega equal to omega naught, okay, in resistor we know VR is IR into R, but what is the current I naught into R? What is I naught? V by R into R. Okay, so VR is V. VR is V. VL is plus J XL into IL plus J omega naught L into IL. IL is I naught. That is V by R now plus J omega naught L by R into V. So, but what is this plus J omega L by R quality factor na? So VL is plus J Q naught into V. Okay, plus J Q naught into V. That is voltage across inductor is quality factor times the supply. Then if I go to capacitor, VC is minus J XC into IC. Minus J by omega naught C, because omega is omega naught now, into IC is I naught. I naught is V by R now. That is minus J into 1 by omega naught RC into V. So this VC is equal to minus J Q naught into V. Minus J Q naught into V. minus j q naught into V. So interestingly, see voltage across inductor and voltage across capacitor is quality factor times the supply voltage. Yes or no? That is why I say this as yes, sir. That is why I say this as yes, voltage amplification. Voltage amplification. Suppose if quality factor is 2, the voltage across inductor and capacitor will be double the supply voltage. See the interesting result. But however, if you apply KVL, VR plus VL plus VC is however V only, because these two are equal but opposite in phase. This VL and VC are equal but opposite in phase. They phase cancel each other. So it will be obviously VR plus VL plus VC is V only. Okay, now V. Okay, that is supply voltage. KVL 100% satisfied. Now, based on these results, I am writing this note. Yes, under series resonance condition, under series resonance condition, the net impedance is minimum. Under series resonance condition, the net impedance is minimum. So current is maximum. Okay, the net impedance is minimum, so current is maximum. Hence it is acceptor circuit. It accepts the signal. Acceptor circuit. See the meaning. What is the meaning I'm trying to say? Under series resonance, the net impedance of the circuit is minimum, so current is maximum. So it is an acceptor circuit. It accepts that signal which is at that frequency under series resonance. Okay. Moreover, at series resonance frequency, at series resonance frequency, the voltages across L and C are quality factor Q naught times, okay, quality factor times Q naught times the supply voltage. Q naught times the supply voltage. Okay. At series resonance frequency, the voltages across L and C are Q naught times the supply voltage. Okay. Hence, this circuit is considered as voltage amplification circuit. Voltage amplification circuit. Voltage amplification circuit. Okay. Yes. Under series resonance frequency, the voltages across L and C are quality factor times the supply voltage. Hence, this circuit is called voltage amplification circuit. Okay. So now, see, sir, 2 points. One way we are saying impedance is minimum, current is maximum, but we should not call this as current amplifier, please. Acceptor only. Why? Because at any instant in series RLC, current is equal in all the elements. We should never call this as current amplifier. I know overall under series resonance, impedance is minimum, current is maximum, but we should not call this as current amplifier. In fact, it is an acceptor circuit, but voltage across L and C are quality factor times the supply. Yes, voltage across L and C are quality factor times the supply. Okay, na? Hence, it is a voltage amplification circuit. So series resonance has two names. One is acceptor, one is voltage amplifier. Remember that. Now I am coming to application. Yes, now I am coming to that application. Yes, that application is based on this point only. This series resonance phenomena. Okay, this series resonance phenomena. Okay, this series resonance phenomena can be used. Okay, na? Can be used in design of analog communication based receivers using passive elements. Why? See the first point here. First point says that under series resonance, the net impedance is minimum, so current is maximum. Current is maximum, that signal it is accepting. That signal it is accepting is the receiver design, sir. So the first point says that under series resonance, the impedance is minimum, current is maximum. So it is acting like what circuit? Acceptor circuit. So this series resonance phenomena can be used in design of analog communication based receivers. Yes, this series resonance phenomena can be used in design of analog communication based receivers using passive elements. Okay. Example. Yes, example is old radios. Old radios. Old radios. Okay. Before transistor technology came. Okay. Old radios before transistor technology came. Okay. Now there is a meaning there. There is a meaning. Okay. There is a very interesting thing that you have to understand. Now let us understand this application. So now we are going to application of series resonance. Application of series resonance. Now, once we understood this point that series resonance circuit, impedance minimum, current is maximum, it acts like an acceptor circuit. Yes, it acts like an acceptor circuit. Now I'm coming to definition of bandwidth. Bandwidth. BW. Bandwidth BW. Okay. Now bandwidth represents the range of frequencies. The range of frequencies. The bandwidth represents the range of frequencies where okay, I will write neatly. Okay, where the power level in the signal, where the power level in the signal is at least half of maximum power, that circuit can handle. This is very interesting, sir. Bandwidth represents the range of frequencies where the power level in the signal is at least half of maximum power that the circuit can handle. Now, sir, let us come to this interesting understanding. So I want everyone to pay more attention here. Everyone, now we are coming to application of series resonance. Yes, we are coming to some interesting applications of series resonance. Okay. Now, what does it mean? See, what does it mean? See, series resonance can be used as an acceptor circuit. Series resonance is used as an acceptor circuit. Okay. Series resonance is used as an acceptor circuit. Okay, na? Yes, as an acceptor circuit. And that is why we are using them in radios, in old radios. Today it is all transistor technology, digital communications. Old technology we are talking. So if you tune the circuit to that frequency, then under resonance, that signal it gets amplified and attracted and accepted, and that radio station we can listen. So now bandwidth. Bandwidth represents the range of frequencies where the power level in the signal is at least half of maximum power that the circuit can handle. So we are now using the series resonance circuit for radios. Yes or no? We are using the series resonance for radios. Okay. Then I should know the bandwidth of this circuit so that I can operate in that frequencies which is provided by the radio service provider. Like bandwidth represents the range of frequencies where the power level in the signal is at least half of maximum power that the circuit can handle. Like in India, all our radios will have bandwidth from 88 megahertz to 110 megahertz, like that. So for series RLC circuit also, if you want to use in communication, we should know the bandwidth of it. Okay, now we should first know the what? We should first know the bandwidth. Okay, so what is that bandwidth? Bandwidth represents the range of frequencies where power level is at least half of maximum power. So now I'm saying that, so at cutoff frequencies or corner frequencies, power should be at least half of maximum. Okay, power should be at least half of maximum. That is nothing but I naught square R by 2. That is nothing but I naught by root 2 square into R. That is nothing but 0.707 I naught square into R. 0.707 I naught square into R. Okay, na? That means what we understood, bandwidth represents the range of frequencies where the power level in the signal is at least half of maximum power that the circuit can handle. So if power is half of maximum power, yes, if power is half of maximum power, current should be at least 70% of maximum. That is the meaning. If power is at least half of maximum power, current should be at least 70% of maximum. That is the meaning. So at cutoff frequencies or corner frequencies where bandwidth we are defining, sir, this power should be at least half of maximum power. That is what the definition is saying. If power is half, current should be 70%. Current graph we know now. That is why see current graph we already know. See, we already did draw current graph. Current versus frequency graph we already know now, sir. That is graph 3. I told you already. This current versus frequency graph is like this. Okay, this current versus frequency graph is like this. Okay, yes, it is like this. Now what we observed at resonance frequency, yes, omega equal to omega naught, current is maximum. Okay, at omega equal to omega naught, current is maximum, which is V by R, that is I naught. Now what is bandwidth? Bandwidth represents the range of frequencies where the power level is at least half of maximum power. If power is at least half of maximum power, current should be at least 70%, I naught by root 2. So if this is I naught, 70% to that, okay na? This is 50, this is 60, 70, 70% to that, okay na? This is 70% to that. I naught by root 2. And this will become lower cutoff frequency, omega 1, upper cutoff frequency, omega 2. And this is called bandwidth. Bandwidth represents a range of frequencies. Yes, bandwidth represents a range of frequencies where power level in the signal is at least half of maximum power. If power is at least half of maximum power, current is at least 70%. Okay, na? Now here I want to write. Here we want to write that omega 2 is called upper cutoff frequency, upper cutoff or corner or roll off frequency. All these are the names. Upper cutoff frequency I will write. But you remember in different books it is called corner frequency or roll off frequency. Omega 1 is called lower or lower cutoff. Lower cutoff or roll off frequency. Okay, upper cutoff frequency, omega 2. Omega 1 is called lower cutoff frequency. Okay, upper cutoff frequency or lower cutoff frequency. Okay, yes, lower cutoff frequency or upper cutoff frequency. Okay. Now we need to derive this bandwidth and other things. So now, because at cutoff frequency or corner frequency, power is half of maximum power, that are the limits. So all frequencies above this 70% of current is power greater than half of maximum. So this is called bandwidth. So bandwidth represents the range of frequencies where power level is at least half of maximum power, that is current is at least 70% and above. That is the meaning there. Okay, that is the meaning there. Okay, na? Yes. That is the meaning that you have to understand. Yes, that is the meaning. Okay, na? So in that regard, now I can continue. That means at corner frequency, power is half. So current is how much? 70%. So let us equate that. So at the cutoff frequencies, cutoff frequency, current is 70% of maximum. So if you equate that, I is V by Z. What is Z? Root of R square plus XL minus XC square. And this I naught is however V by R. V by R. Okay, now if you remove these things and square and cross multiply, you will get omega L minus 1 by omega C square is equal to R square. From that I will get omega L minus 1 by omega C. Yes, you will get it as plus and minus R. So there are two such frequencies. There are two such frequencies where current is at least 70% of maximum. See clearly, current is 70% of maximum at two frequencies. Now that is why two possible answers came. But how to decide the value then? Now we know at omega equal to omega 2, if you take this is omega 2L minus 1 by omega 2C. Okay, if you put here omega 2L minus 1 by omega 2C is plus R, I will take. This is very interesting. Similarly, at omega equal to omega 1, that is lower cutoff frequency, omega 1L minus 1 by omega 1C is equal to minus R, is equal to minus R. That is B. Okay, yes, that is B. Okay, at omega equal to omega 2, yes, at omega equal to omega 2, that is plus R. and omega equal to omega 1 minus r. Okay, minus r. How this came? Now you may say, sir, here two solutions are possible, but at upper cutoff frequency, why you took plus r and lower cutoff frequency minus r? Now these concepts come from, yes, I will write here, from graph 2. You see now graph 2 that will tell the secret. Graph 2, that is, this is coming from graph 2. Okay, graph 2 reactance. Now I will tell there. Okay, if I go to graph 2, yes, if I go to now graph 2, see here graph 2. Now clearly here, at resonance frequency, net reactance is 0. But for frequency greater than resonance frequency, net reactance is positive. For frequency greater than resonance frequency, net reactance is positive. That means for at upper cutoff frequency, net reactance is positive. At upper cutoff frequency, net reactance is positive. So automatically, if you observe, yes, at upper cutoff frequency, net reactance is positive. Now this is XL minus XC. Net reactance only, na? That should be positive. That is why I took what? Plus R. That is why I took what? Plus R. Okay, na? Then at lower cutoff frequency, that is omega less than omega naught, reactance is negative. At lower cutoff frequency, that is omega less than omega naught, reactance is negative. Yes, reactance is negative. Okay, na? Yes, that is why minus R. That is why minus R. Okay, na? So now if I do that, yes, now everyone, after understanding these two, everybody, now you see, now after understanding these two, now first I am adding A plus B. First I will add A plus B. If I add A plus B, everybody, if I add A plus B, that is L into omega 1 plus omega 2. Okay, L into omega 1 plus omega 2. Okay, and this part also if I add minus 1 by C into, okay, omega 1 plus omega 2 by omega 1 omega 2 equal to 0. That is plus r minus r is 0. So if you remove this, yes, if you remove this, now what you will get, this L equal to 1 by C omega 1 omega 2. So omega 1 omega 2 equal to 1 by LC. But 1 by LC is nothing but omega naught square. So omega naught square is equal to omega 1 omega 2. So omega naught is root omega 1 omega 2. So F naught is root F1 F2, which is called what? Geometric mean. This relation is called geometric mean. It is called geometric. Okay, which is called what? Geometric mean. That is the mean. So F naught is root F1 F2, which is called geometric mean. Okay, now geometric mean we call. Okay, so resonance frequency is geometric mean of cutoff frequencies or corner frequencies. Okay, now bandwidth. Now I'll do A minus B also. Now bandwidth, I know what is the bandwidth? I already told in the graph. Bandwidth is this omega 2 minus omega 1. That bandwidth I want. Okay, now for that bandwidth, I will do now A minus B. If I do the difference of these two, A minus B. Okay, if I do the difference, so if I do A minus B, if I take L common, L into omega 2 minus omega 1 if you take common, then here if you take plus 1 by C, again you will get omega 2 minus omega 1 by omega 1 omega 2 is 2R. Now if you take that omega 2 minus omega 1 as common, which is bandwidth, L plus 1 by C into omega 1 omega 2R. That is omega 2 minus omega 1 into L plus 1 by C into omega 1 omega 2. That is 1 by LC. Omega 1 omega 2 is 1 by LC. Now see, we got here already. We got that relation already. So omega 1 omega 2 is already 1 by LC. So if I put there, yes, is equal to 2R. So yes. Now this omega 2 minus omega 1 2L equal to 2R. 2L equal to 2R. So I say now omega 2 minus omega 1, this is bandwidth na, R by L. I told us that this chapter is highly mathematical. That's why relax and listen. Just relax and listen, learn now only. So now, so I say bandwidth. Bandwidth BW, that is omega 2 minus omega 1 R by L radians per second. F2 minus F1 is R by 2 pi L hertz. I'm writing a conclusion that yes, bandwidth is proportional to resistance, but resonance frequency is independent to R. Okay, bandwidth is proportional to resistance. See here, F2 minus F1 or omega 2 minus omega is proportional to R. So bandwidth is proportional to R, but resonance frequency is independent to R. Okay, bandwidth is proportional to R, but resonance frequency is independent to R. Now from this discussion, now we can get the most accurate value. This is a gate bit again. Yes, gate bit. The most accurate values of omega 1 and omega 2. Let us do that. Okay, the most accurate values of omega 1 and omega 2. So now in that regard, if I go, first of all, we got the difference. That is the bandwidth we got now. Omega 2 minus omega 1. Okay, that is how much R by L we got. Let us say equation 1. And we got omega 1, omega 2 also. What is omega 1, omega 2? 1 by LC. 1 by LC also we got. So we got the difference, we got the product. Then automatically, what is omega 2 plus omega 1? That is root of omega 2 minus omega 1 square plus 4AB. Okay, so we know A plus B is root of A minus B whole square plus 4AB. That is 3. But here, indirectly, this omega 2 plus omega 1, what it becomes now if you substitute, that is root of this omega 1 minus omega 1 square is R square by L square. And this becomes how much? Plus 4 by LC. Yes or no? 4 by LC. Because omega 2 minus omega 1 is R by L whole square. And 4 into omega 1, omega 2. Omega 1, omega 2 is 1 by LC now. Yes, that is 1 by LC. Okay, that is 1 by LC. Okay, now if you solve 1 and 3, finally, if you solve 1 and 3, yes, if we solve 1 and 3, we get. Okay, okay. Okay, that is radians per second. Then omega 2 will be plus R by 2L. Okay, R by 2L square plus 1 by root LC square. So these are all in radians per second. This is important, sir. This question came. So after getting the difference and product, we got the sum. But substitute, now solve this 1 and 3. How? Because A minus B, A plus B. You add it and like that you do, you will get this. So remember, sir, you can also get this by solving the characteristic equation of series RLC. That is also understood. But these are the critical frequencies or cutoff frequencies where the magnitude of current is 70% of maximum. Okay, now IES. In IES, what they are asking in IES, another interesting thing is if quality factor is very, very high, like quality factor is greater than or equal to 10. Okay, if quality factor is greater than or equal to 10, okay, if quality factor is greater than or equal to 10, then current versus frequency graph, okay, becomes very narrow with steep characteristics. Okay, very narrow and steep. Okay, steep. Then following approximated mathematical relations exist. Approximate mathematical relations exist. So what I'm trying to say, if quality factor is very, very high. Now how quality factor is related to this, I will explain to you. But one thing it happens that this curve becomes very narrow and steep. This curve becomes very narrow and steep. At omega equal to omega naught, this becomes I naught. And again, if I take this 70% here, if I take this as 70%, omega 1, omega 2. Now, because this became very narrow and steeper, now the approximate relations are this total is bandwidth, I know, but because it is very narrow and very, very nearer, he is approximating this half as bandwidth by 2 and is approximating this half as also another bandwidth by 2. That is the biggest approximation. Okay, so everybody, I will explain again. Just go through this. I will explain again. Everybody see now, if quality factor is very, very high, then current versus frequency gap. Now, how this is related to bandwidth knowledge and see, first of all, what is the meaning of high quality? High quality means, yes, high quality means less losses. Less losses means less resistance. See, but bandwidth is proportional to resistance. Now, see how it is linked, listen carefully. See, high quality, everybody raise your hand, are you there? Everybody should raise the hand. Now I got more than 160 students here. Everybody. Yes, sir. Please stay focused, sir. I want you to be here. Everybody, please. Okay. So now put down your hands. Everybody, put down your hands. Yes, put down your hands now, everybody, because it keeps popping out now and then. Okay. Everybody, put down your hands. See, this chapter is like that, sir. Please understand. Okay, now this chapter is a highly mathematical chapter, sir. But it is a part of AC study state. And what sort of gate bits here and there, I'm covering everything. All gate bits and IS bits, I'm covering. Okay, now I will keep everything at one place, sir. Read my notes. No need to touch anything. And only for practice, go for IS bits and gate bits. Even in gate and IS bits, I'm doing most of them here only. Sure, now in that regard, everybody. Yes, now in that regard, I want everyone to please observe here. Yes, I want everyone to please observe here. See, what I'm trying to say is, yes, everybody, what I'm trying to say is, here, how quality factor is related to the width of the curve. Why? Because quality factor high means, see, I told you here, if quality factor is very high, curve becomes narrow and steep, narrow and steep. What is the reason? Because quality factor high means losses are less. Losses are less means resistance is less. Quality factor high means losses are less. Losses are less means resistance is less. Resistance is less means bandwidth is also less. Resistance is less means bandwidth is also less. Okay, bandwidth is also less. Okay, na? Chalo, resistance is less means bandwidth is also less. So automatically, yes, automatically, you see, if this is very, very narrow, he is approximating this as bandwidth by 2, bandwidth by 2. Actual relation is, we know, yes, resonance frequency is geometric means of cutoff frequency, but approximately is telling arithmetic mean. So now we can say what? Now we can say mathematically. Now we can say mathematically that omega naught minus omega 1 is bandwidth by 2. Bandwidth by 2. That implies omega 1 is omega naught minus bandwidth by 2. Omega 1 is omega naught minus R by 2L. That is F1 is F naught minus. Okay. F1 is F naught minus R by 4 pi L hertz. Okay, R by 4 pi L hertz. Now also if I take omega 2 minus omega naught, omega 2 minus omega naught is bandwidth by, that is omega 2 is omega naught plus bandwidth. Okay, see omega 2 minus omega 1 is also bandwidth by 2. So, okay, here what I can write here, you see omega 2 minus omega naught is also bandwidth by 2. Okay, so automatically omega 2 is this, but there is nothing but omega naught plus r by 2l, or f2 is f naught plus r by 4 pi l hertz. One is in radians per second and one is in hertz. So these formulas are also asked in IS, sir. These two formulas were asked in IS. Okay, that you remember. Okay, but when this is valid graphically if quality factor is very, very high. Okay, now keep remembering doubts, sir. You put a separate book at least for doubts. You note down the slide number if slide number is there, or you can tell which area it is coming, like that. Okay, at least do that. Okay, at least do that. Okay, that favor you do to me. Okay, you keep down noting down which area the doubt is coming, and all you ask me. Okay, even after entire course is over, I will give my WhatsApp number. You can put the screenshot. I will tell. Okay, don't worry about that. Okay, but take time, sir. It is that you have to understand finally. Though I'm explaining my side, your understanding and your, okay, interpretation is very, very important. Okay, na? Now I'm going to another interesting gate bit. Chalo, this gate bit everyone should tell. Okay, na? This gate bit. Determine power factor of series RLC circuit. Okay, determine the power factor of series RLC circuit at lower and upper cutoff frequencies. Okay, determine the power factor of series RLC circuit at lower and upper cutoff frequencies. Okay, determine the power factor of series RLC circuit at lower and upper cutoff frequencies. Chalo, everybody do this now. Determine the power factor of series RLC circuit at lower and upper cutoff frequencies. Okay, now see this everybody. What is the power factor of series RLC circuit at lower and upper cutoff frequency? Okay, na? So let us understand this. First of all, for series RLC circuit, everybody, what is impedance? Impedance is R plus J XL minus XC. Yes or no? Now first A bit. At omega equal to omega 1, which is lower cutoff frequency, then this Z becomes R plus J. This is omega 1L minus 1 by omega 1C. But sir, this is net reactance. Now that net reactance at lower cutoff frequency, yes, that net reactance at lower cutoff frequency is minus R. Nah, this is minus R. So this is really minus R. See, we already got this somewhere. You see here now. See, I will tell you. Yes, you see at lower cutoff frequency, net reactance is minus R. Nah, this again we got from graph 2 only. Yes, minus R, minus R. So it is what nature? RC nature. Negative reactance means RC. That net reactance value is minus R, but negative reactance means RC nature. So from that what I can write? From that what I can write? Power factor is, yes, from that what I can write? Yes, power factor is R by Z. R by Z. That is R by root of R square plus R square. That is 1 by root 2. 1 by root 2 is 0.707 and it is leading 0.707 leading 0.707 leading. Then second bit, at omega equal to omega 2 upper cutoff frequency, Z is R plus J. Now see this, sir. This is omega 2L minus 1 by omega 2C. But what is the net reactance at omega equal to omega 2? It becomes plus R. Plus R. It becomes plus R. Then automatically what is the power factor? Power factor is R by Z. R by Z. That is R by root of R square plus R square. That is 1 by root 2. That is 0.707. This is lagging because net reactance positive. Net reactance positive lagging. Net reactance positive lagging. Okay, na? That is very, very interesting. So what are the answers? At lower cutoff frequency is 0.707 leading and upper cutoff frequency is 0.707 lagging. Okay, na? Now I am giving another IES objective. Chalo, IES objective. Everyone should tell me IES objective. Determine the relation between quality factor and damping ratio in series RLC circuit. In series RLC circuit. Okay, determine the relation between quality factor and damping ratio. Chalo, quick sir, 1 minute only. Now, see, this is very interesting link between network theory and control system. See, quality factor is what? 1 by R root L by C. And damping ratio zeta is what? R by 2 root C by L in a series RLC. So, conclusion is Q naught is 1 by 2 zeta or ulta, or I can also write like zeta is 1 by 2 Q naught. Both are same. That is the meaning here. That is something very, very, very interesting. Okay, na? That is the meaning that you have to understand. Okay, na? There is a relation between quality factor and damping ratio. Okay, that is the same meaning here. I am giving another gate question. Okay, determine resonance frequency of circuit below. Determine resonance frequency of circuit below. Eight. 2 farad, 1 Henry, 1 ohm. Chalo, everybody determine the resonance frequency of the circuit below. Yes, everybody see resonance frequency. Now, for that, what I will do, I will find impedance and equate the net reactance to 0. So, first of all, what is the impedance here? Now, if I go with impedance, yes, everybody see now, if I go with impedance, first is a capacitor minus J by omega C plus R and L are parallel. 1 in parallel to plus J omega L. L is 1. Okay, L is 1. Okay, now. So, that is nothing but minus J by 2 omega plus 1 in parallel to j omega. So this into this by this plus this. Okay, now we'll rationalize this. I will rationalize this. This into 1 minus j omega by 1 minus j omega. So if you observe, yes, if you observe everybody, yes, this z will be minus j by 2 omega. Okay, and now if you observe this, this is omega square minus j omega by a plus b into a minus b, a square minus b square. So z is now real part, omega square by 1 plus omega square plus imaginary part. This is plus j omega, you can check it. See, j omega plus omega square. Okay, na? J omega plus omega square and denominator is this. So if you take here, omega by 1 plus omega square minus 1 by 2 omega. Minus 1 by 2 omega. Okay, now you know this is net reactance. This is net reactance. Now under resonance we know. Yes, now we know under resonance. Now we know under resonance. Yes, at omega equal to omega naught under resonance. At omega equal to omega naught under resonance, net reactance is 0. Net reactance is 0. So net reactance is 0. So if I do that, omega naught by 1 plus omega naught square is equal to 1 by 2 omega naught. So 2 omega naught square is equal to 1 plus omega naught square. Omega naught square is 1. Omega naught is 1 radians per second. That is the answer. Okay, now answer is 1 radians per second, sir. So that is the resonance frequency. That is the resonance frequency. Okay, now. Now there is something called selectivity. Selectivity S. Okay. Now this bit also came in GATE and IES. Okay, what is the meaning? Now this comes from communication. Actually, this term comes from communication. What is that? Yes. Selectivity. Selectivity is the ability. Selectivity is the ability of a communication network. Communication network. Okay, selectivity is the ability of a communication network, okay, to discriminate or distinguish. Okay, discriminate or distinguish between desired and undesired frequency. Undesired frequency or frequencies. See the meaning. Selectivity is the ability of a communication network. See, selectivity is the ability of a communication network to discriminate or distinguish between desired and undesired frequency. Okay, selectivity is the ability of a communication network to discriminate or distinguish between desired and undesired frequencies. Okay, selectivity is the ability of a communication network to discriminate or distinguish between desired and undesired frequency. Now, mathematically, okay, mathematically, selectivity is resonance frequency by bandwidth. Okay, so resonance frequency by bandwidth, that is F2 minus F1. Now in series RLC circuit, resonance frequency is 1 by 2 pi root LC by bandwidth is R by 2 pi L. So if you remove these unnecessary things, so this will come as 1 by R root L by C. But what is this 1 by R root L by C? Quality factor. So automatically selectivity is quality factor under resonance. Selectivity is quality factor under resonance. Okay, selectivity is quality factor under resonance. Okay, and also we know selectivity is inversely proportional to band. Okay, these bits were asked in IES and GATE. Okay, na? Yes, that you remember. Okay, with this series resonance is perfectly over, sir. With this, what is over? The series resonance is perfectly over. Okay, I can say with this series resonance is perfectly over. Okay, now let us go further, sir. This is very, very interesting now. Okay, once you know series resonance, yes, now let us go to topic 2 here, parallel resonance. Parallel resonance. Okay, in that first general parallel circuit. General circuit. Because in parallel there are three important circuits. Huh? First I am taking the general circuit. Easy to learn now because we already understood series resonance. With dual duality I can teach now parallel resonance. This is voltage, this is total current, this is RLC, this is RLC. Now we know that at resonance, yes, we know that at resonance, V and I are in phase. V and I are in phase. Okay, at resonance, V and I are in phase. Phase angle phi is 0, unity power factor. Total admittance is conductance. Total admittance is conductance. Okay. Yes, in parallel resonance, okay, circuit, it is a general parallel RLC circuit. We know under resonance, V and I are in phase. Phase angle phi is 0, unity power factor, and total admittance is conductance. Now in parallel circuit, admittance is the faster way, sir. So let us find the total admittance. Okay, now we know this total admittance is admittance of R branch plus admittance of L branch plus admittance of C branch. Because they are parallel now, we can add them. That is 1 by R. This is 1 by plus JXL. This is 1 by minus JXC. So this Y total will be 1 by R. This you take up, this becomes minus J by XL. This is plus J by XC. So this Y total will be 1 by R plus J into 1 by XC minus 1 by XL. Okay, 1 by XL. Okay. So now this is called net susceptance. Yes or no? Now we know that. Now we know that. Yes, at resonance. At resonance. At resonance where omega equal to omega naught. Net susceptance is 0. At omega equal to omega naught, net susceptance is 0. So what I will do now, I will equate that. That implies 1 by XC is equal to 1 by XL. That implies XL equal to XC. What does it mean? Omega naught L equal to 1 by omega naught C. Omega naught is 1 by root LC. Radians per second. F naught is equal to 1 by 2 pi root LC hertz. One by 2 pi root LC hertz. Okay, so here also interestingly we got the same formula. Formula is same, but the circuit is a parallel circuit. Its behavior is completely different now. Okay, na? So now here also first graph 1. What is this graph 1? Yes, net admittance versus frequency. Now what is net admittance? Root of, this is 1 by R square, BC, that is omega C, minus BL, 1 by omega L square. You see this admittance only I am writing here. See, this magnitude 1 by R square, but 1 by XC, that is 1 by omega C and minus 1 by omega L. Now if I plot this graph again, it will come something like this. If I plot this graph, it will come somewhere like this. At resonance frequency omega naught. Yes, exactly at resonance frequency omega naught. Okay, this is Y is G, which is minimum. Y is G, which is minimum. You see now at omega equal to 0, this is something by 0 infinity, and omega infinity also, this becomes infinity. Only at omega equal to omega naught, net susceptance is 0, admittance is minimum. Okay, then graph 2. Graph 2. Graph 2 is net susceptance versus frequency. Net susceptance versus frequency. Net susceptance versus frequency. Now if you observe susceptance versus frequency graph, first let me write the equation. we know net susceptance is what we got here. You see now 1 by xc minus 1 by xl. Okay, that will be coming something like omega c minus 1 by omega l will come. Now if I plot that, positive susceptance 0, negative susceptance, omega c, this is omega c, this is minus 1 by omega l. Minus 1 by omega. Now there is a frequency where both are equal. Okay, these both are equal. Okay, resonance frequency net susceptance is 0. Now the combination of these two graphs, yes, the combination of these two graphs is this yellow color line, which is net susceptance. Net susceptance. Now from this very clear that at resonance frequency net susceptance 0, purely resistive, so unity power factor. But for frequency less than resonance frequency, yes, everybody watch this, for frequency less than, so at resonance frequency unity power factor means this also, if you observe that at resonance frequency it is purely resistive, the nature of the circuit is purely resistive. Then for frequency less than resonance frequency, now for frequency less than resonance frequency, yes, everybody, for frequency less than resonance frequency, net susceptance negative. Net susceptance negative means RC circuit. Okay, it is RC now. This is RC circuit. Okay, this is RC circuit. Okay, RC circuit behavior. So this is leading power factor. Leading power factor. Let me correct it, sir. Everybody, please correct it. See what I want to argue. Susceptance negative na RL only. Okay, let me correct it. See, sir. Let me repeat, everyone. See, first of all, at resonance frequency, net susceptance 0, so purely resistive, unity power factor. Now see now, frequency less than resonance frequency. Yes, for frequency less than resonance frequency, susceptance negative, sir. Susceptance negative means inductive, inductive, RL circuit. So this becomes what? Lagging power factor, lagging. And for frequency greater than resonance frequency, net susceptance is positive. Susceptance positive means, yes, susceptance positive means RC circuit. This is RC circuit. This is leading power. Leading power. Leading power. Okay. For frequency equal to resonance frequency, unity power factor resistive, less than resonance frequency, susceptance negative RL, lagging power factor, frequency greater than resonance frequency, RC leading power factor. Okay, that is the meaning. RC leading power factor. Okay, now that is the meaning there. Okay, now after understanding is graph 2, now current graph. Yes, graph 3. Yes, graph 3. Current versus frequency. Okay, current versus frequency. But here in parallel, I is V by Z or V into Y. V into Y. Okay, V into Y. That is V into Y is root of 1 by R square plus omega C minus 1 by omega L square. So as admittance is minimum, current is minimum at resonance frequency. Yes, this is direct relation. Okay, this is directly from mathematics. I can understand that if you plot current versus frequency graph, yes, current versus frequency graph. Yes, this is going to be ulta. Rejector circuit we call filter design rejector circuit, where at resonance frequency omega equal to omega naught. This is minimum, current is minimum, I is minimum. Okay, that is very, very interesting. Okay, that is very interesting. Okay, this is a rejector circuit because you see now here, clearly here also, at 0 frequency, something by 0 infinity. At infinity frequency also infinity current. But at resonance, net susceptance is 0, admittance is minimum, so current is also minimum, like that. Okay, now that is very interesting graph. Now I am drawing the phasor diagrams. Okay, now I am drawing the phasor diagrams. Now phasor diagrams. Phasor diagram for all the cases. First, case 1. Case 1. Omega less than omega naught. For omega less than omega naught, you know Y is G minus JB net. Y is G minus JB net. So omega less than omega naught, Y is G minus JB net. Yes, G minus J B net. That means net susceptance negative inductive. Inductive. So it is an parallel RL circuit nature. In parallel RL, I lags V by 5. It is lagging power factor. Lagging power factor. But in my notation, with respect to voltage, current lags. With respect to voltage, current lags. Okay, and this is phase angle phi. So automatically here, phi is negative. Phi is negative. Now when I come to case 2, omega equal to omega naught, y equal to G. So purely resistive. Purely resistive. I in phase with V, phi is 0, unity power factor. So with respect to voltage, current is in phase. So phi is 0. 0 degrees. Phi is 0 degrees. Case 3, omega greater than omega naught. So y is G plus JB net. RC circuit leads V by 5 degrees. Leading power factor. Now leading power factor means with respect to voltage. Yes, with respect to voltage, current will lead. 5 degrees. So obviously, phi is positive. Okay. So now complete. Yes, if you observe now, yes, graph 4. Graph 4, that is okay, phase angle versus frequency. If I go to graph 4, phase angle versus frequency. This is 0, this is plus 90, this is minus 90. Okay. So as you increase the frequency from 0 to infinity, yes, as you increase the frequency from 0 to infinity, phase angle is going from negative to positive. Okay, phase angle is going from negative to positive. So this is a resonance frequency. Unity power factor, here it is lagging power factor. Lagging power factor, here it is leading. Okay. Now I'm drawing the complete phasor diagram. Same pattern, sir. Complete phasor diagram. Complete phasor diagram. See, complete phasor diagram means it is for all the parameters. So I'm taking the standard parallel RLC circuit. So and I'm also including this IR, IL, and also IC. Now we know that, yes, now in parallel circuit, what is better to take as reference? I will take voltage as reference. I will take a voltage as reference. So now we know at resonance, yes, at resonance. Yes, at resonance, what we know first of all, inductive susceptance is equal to capacitive susceptance. When susceptances are equal, when both susceptances are equal, okay, na, inductive susceptance is equal to capacitive susceptance. When susceptances are equal, okay, na, everybody, okay, when susceptances are equal, net susceptance 0. But in parallel, already voltages are equal. When voltage, because parallel voltage is same now, voltage equal, susceptance equal, so currents also must be equal. Currents also must be equal. Now, with respect to voltage, which current is in phase? IR is in phase. IL lag. Okay, IC lead. IL add IC. Both are equal but opposite. Both are equal but opposite. Because yes. Now if you do the KCL, phasor sum of IR plus IC plus IL is I only. So is I only. That is I. And phase angle phi is 0 altogether. Chalo, conclusions are, first of all, I is IR, phi is 0, and power factor is 1. Power factor is 1. That is a big confusion. Okay. Now, sir, I'm asking interesting question now. Okay, now I'm asking some interesting question. Okay, how this circuit will behave? That is very, very interesting. Okay, I'm asking some another interesting question. Okay. Now, how this circuit will behave? See, suppose if you take this pure LC combination. Yes, you see this now. If you take pure LC alone, under resonance, net susceptance 0. Susceptance 0 means reactance is infinity. Understand, sir? Susceptance 0 means reactance infinity. Reactance infinity means open circuit. Yes, the pure LC segment acts like open circuit. That's why total current will flow only through resistor. Total current will flow only through resistor, but this is acting like open circuit. So source is supplying energy only to resistor. So under resonance, this pure parallel LC segment is like open circuit. Total supply current flows only through resistor, and source is supplying energy only to resistor. Then how LNC are working then? Then how LNC are working? LNC are working. How? By exchanging the magnetic and static energies between them. Now that is interesting, sir. Here also, if you observe carefully, yes, I am writing this very important note that at parallel resonance condition. Yes, resonance condition. Yes, at parallel resonance condition, the pure parallel L and C together acts as open circuit. Open circuit. L and C acts together as an open circuit. Okay. And source is supplying energy only to resistor. And source is supplying energy only to resistor. However, L and C components work together by exchanging the stored electromagnetic energy and electrostatic energy between them in an oscillatory phenomenon. Okay, you understand the meaning here. However, the L and C components work together by exchanging the stored electromagnetic energy and electrostatic energies between them in an oscillatory phenomenon. Now, this question, yes, the frequency of this energy oscillations is 2 omega naught or 2f naught. 2f naught. This is important. But for parallel RLC also, f naught is how much? 1 by root L. See, here also same way, sir. If you expand this, if you project the phasor, we get sinusoids now. I told you the meaning. So this is now voltage as reference. Current. This is current now. IR, which is also equal to I. IR, which is also equal to I. This is IR, which is also equal to I. Then voltage, current through capacitor, it will lead voltage by, yes, it will lead voltage by 90. Okay. Then current through inductor will lag voltage by 90. Okay. So then this is like 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. So here also if you observe at 0 degrees, half Li square is maximum, because negative maximum na half Li square is maximum. So EL is maximum. If you observe, yes, if you observe carefully, inductor energy and capacitor energy at 0 degrees, half Li square is maximum. But half CV square is 0 because voltage across capacity supply only, that is 0. Then at 90 degrees, what happened? 90 degrees, what happened? Half Li square is 0, but half CV square is maximum. Then at 180 degrees, see for capacitor C its voltage and for inductor C inductor current. And again at 180 degrees, half Li square is maximum. Yes, half Li square is maximum, but half CV square is 0. At 270 degrees, again half Li square is 0, but half CV square is maximum. Then at final, after one cycle, 360 degrees, half Li square is maximum, but half CV square is 0. So energy is oscillating from inductor to capacitor, capacitor to inductor, inductor to capacitor, capacitor to inductor. And this frequency of oscillation is 2 times, because 2 times, see for one cycle of supply 2 times, but already this supply is at what frequency, resonance frequency. So this will be 2F naught. That is very, very, very interesting observation. Okay, very interesting observation. Okay. That is a very, very important observation. Now I can write from circuit. I'll give break in few minutes from circuit. Today I need to go, please. From circuit, what we can say? Yes, from circuit we can say V is I Z. But this Z I will write it as 1 by Y. So automatically, yes, automatically this is, yes, I by, what is Y? Root of 1 by R square plus omega C minus 1 by omega L square. Okay. Now at omega equal to omega naught, net susceptance is 0. So that implies if net susceptance is 0, V is I by root of 1 by R square plus 0 square. So V is IR. V is I into R. Okay. And we know this current is already minimum. We already plotted the graph now, sir. Current is minimum only. Yes or no? You see the graph. Current is already minimum. We got the current graph now, sir. Current graph is already minimum. Okay, we know that minimum. Okay, current graph is minimum. Now at omega equal to omega naught, IR is VR by R. That is V by R. V is IR by R. IR is I. L. IL is VL by plus JX. That is V by plus J omega naught L into, yes, but V is what? IR. Plus J in the numerator, 1 angle 90, you take up 1 angle minus 90, minus J by 1 by omega naught L R into, okay, we know that this is what? V is IR na, V is IR na. So this is R, I will write here, by omega naught L into I. But this is the quality factor of parallel RL combination na. So if I write this IL minus J Q naught into I, where Q naught is a quality factor of the circuit here. If I go to C, IC is VC by minus JXC. That is VC is V by minus J by omega naught C. This minus J 1 angle minus 9, you take up plus J. This become omega naught RC into I. That implies IC is plus J Q naught into I. Okay, what is this? This is called, yes, this is called current amplification. Clearly, this is called current amplification. Current amplification. Same are like series, there it was voltage. So if you still apply, see, that means current through inductor and current through capacitor under parallel resonance condition is quality factor times the supply. Quality factor times the supply. Okay, yes, it is very clear that it is quality factor times the supply. But however, if you apply KCL, IR plus IL plus IC is I only. IR plus IL plus IC is I. Because IL and IC are two equal but opposite. They phase cancel. So IR plus IL plus IC is I only. Okay, na? Now I am writing conclusion here. Yes, the conclusion that at parallel resonance condition, yes, a parallel resonance condition, the net admittance is minimum. Okay, so current is also minimum, hence it is what circuit? Rejector circuit. Hence it is a rejector. Current minimum means it is not accepting, hence it is a rejector circuit. Parallel resonance frequency, the currents through L and C components. Yes, the currents through L and C components are quality factor times the supply current. Quality factor times the supply current. Okay, hence this circuit is considered as current amplification circuit. So two important names, sir. One is rejector, one is current amplifier. See, one way we are telling in parallel resonance, admittance is minimum, current is minimum. One way we are saying admittance is minimum, current is minimum, it is a rejector circuit. But on the other hand, the currents through L and C is quality factor times. But we should never call this as voltage amplifier because voltage is always constant, sir. Here, parallel NASA voltage is always constant. Parallel voltage is always constant. So we should never disturb that. Yes, parallel voltage is always constant. We should never disturb that. Okay. Parallel resonance condition, net admittance is minimum, so current is also minimum. Hence, is a rejector circuit. And at parallel resonance frequency, the currents through L and C are quality factor times the supply current. Hence, circuit is considered as what? Current amplification circuit. Okay, current amplification circuit. Okay, na? There is a meaning there. Now, that conclusion I am writing here. Okay, now this application, just I am giving breaks, sir, but listen, this application I am writing, but still this chapter is not over. This parallel resonance phenomena, can be used in design of band stop, yes, band stop filters, passive filter or band rejection filter, band stop filter, or we say band rejection filter because it is rejector, na, sir. So if you observe the characteristics, current versus frequency characteristics, if you observe, these frequency characteristics are coming like this. So this is omega naught. This is I minimum. This is root 2 times of I minimum. Root 2 I minimum. And this is lower cutoff frequency here. And this is upper cutoff frequency. But this is called stop band. Ulta to bandwidth. This is called what? Stop band. See a rejector, na, sir. This is ulta to bandwidth. But this is called what? Stop band. Stop band. Now here if you solve that equation, omega 1 will come as minus 1 by 2 RC plus root of 1 by 2 RC square plus 1 by root LC square. And omega 2 is plus 1 by 2 RC plus root of 1 by 2 RC square 1 by root LC square. Okay. and the stop band is finally the stop band, that is omega 2 minus omega 1. If you do, yes, you will get it as 1 by RC, radians per second. This I will explain again. Shall everybody, I am taking a break now. See, we'll take 15 to 20 minutes break. 15 to 20 minutes, come back by 11:40. Everybody come back by 11:40. Okay now, come back by 11:40 please. Everybody come back by 11:40. I will decide when to close. Please come back by 11:40. Yes, everybody please come back, raise your hand. Everybody please come back, raise your hand. Okay, see, this last point I want to review. See, after understanding all this about parallel resonance, that we showed that, yes, here current is minimum. So it is acting like rejector circuit. And we observe that rejector circuit, that is very important. So current is minimum rejector circuit, and we observe that current through inductor and capacitor is quality factor times the current. Okay, so based on that, this application. Now this topic, however, I am going to teach in transient chapter. When I go to parallel RLC circuit characteristic equation, there I will derive this also. But otherwise, remember these formulas. Directly remember these formulas. Okay. Here the lower cutoff frequency, upper cutoff frequency, these are the formulas. But here it is called stop band, ulta to bandwidth. In series RLC it is acceptor, we call bandwidth. But here it is called stop band. Okay. That is the meaning. That is a big difference you should know. Now in parallel circuit, there are more interesting circuit configurations. Okay. That is practical. Okay. Practical parallel resonance circuit, which is called tank circuit, which is called what? Tank circuit. Practical parallel resonance circuit, which is also called tank circuit. Okay, now this is called tank. Its performance is similar, but it is more accurate in mathematical modeling. See, its performance behavior is same like parallel RLC, but this is more practical in modeling the losses. This is R, L, and C. Now, here again to get the resonance frequency, I'll find total admittance, like admittances in parallel, admittance of branch 1 plus admittance of branch 2. Branch 1 is RL and branch 2 is pure capacitor. So now this admittance, this is 1 by R plus JXL, and this is 1 by minus JXC. Okay. Now if you rationalize this, Y total will be, okay, this is R minus JXL by R square plus XL square, and this is J by XC. Now if you go by Y total, this is R by R square plus XL square plus J into 1 by XC minus XL by R square plus XL square. Now this is called net susceptance. Okay, this is called net susceptance. Okay, this is called net susceptance. Now we know at resonance, at omega equal to omega naught, that is resonance condition. Okay, resonance frequency or resonance condition, net susceptance has to be 0. Okay, now this is what I am using. Now if I equate that to 0, that implies 1 by XC is equal to XL by R square plus XL square. See, that is what I am trying to do here. Okay, now, yes, you get this. That is R square plus XL square is equal to XL into XC. That is omega naught L into 1 by omega naught C. So if you remove that, yes, you will get this as R square plus XL omega naught L square is equal to L by C. Okay. Okay, I will write like this first, then I will expand, because this is also important conclusion. That is R square plus XL square is L by C. Okay, this is important conclusion. Now if I expand this, R square plus XL is omega square, L square is L by C. See, from that resonance frequency is coming. Okay, from that resonance frequency is coming. So this omega naught square is, okay, yes, this if you take L by LC, yeah, L by C by L square is 1 by LC minus R square by L square. So omega naught is root 1 by LC minus R square by L square radians per second. And F naught is 1 by 2 pi root 1 by LC minus R square by L square hertz. Okay, na? So this is the resonance frequency of what circuit? Practical parallel circuit or tank circuit. Then now third circuit I am going, which is called ideal tank. This is only a concept. What is ideal tank circuit? In ideal tank circuit, R is 0. Okay, in ideal tank circuit, R is 0. So pure LC in parallel is called ideal tank. Remember, sir, this is a very interesting concept. Pure LC in parallel is called tank circuit, ideal tank circuit. So wherever you see network theory, when you get pure parallel LC, wherever you get pure parallel LC, there is a wonderful concept that you have to remember. So this is overall V and overall I. So again, to find total admittance and then resonance frequency. So admittance is in parallel. Admittance of branch 1, admittance of branch 2 in parallel can be added. But branch 1 is pure inductor and branch 2 is pure capacitor. This is 1 by plus JXL. This is 1 by minus JXL. You rationalize this. So this Y total will be into J by J. Okay, this is like minus J by XL. Okay, this is plus J by XC. So this Y total is plus J into 1 by XC minus 1 by XL. Now we know that at resonance, omega equal to omega naught. Net susceptance is 0. Net susceptance is 0. Now if we equate the net susceptance to 0, 1 by XC is equal to 1 by XL. That implies XL equal to XC. Omega naught L equal to 1 by omega naught C. Then I can say this omega naught square is 1 by LC. Omega naught is equal to 1 by root LC, or F naught is 1 by 2 pi root LC. F naught is 1 by 2 pi root LC hertz. Okay. That is the problem. Okay, same thing you will get. Now, this is the most practical. That is here also parallel resonance circuit. Everyone should understand parallel resonance circuit. Yes, parallel resonance circuit. Okay, including losses, including complete losses. That is the most accurate. That means here now I will take both RL and also RC. RL and also RC. This is including losses, sir. This circuit is including losses. RLL, R suffix CC. This is including losses. Including losses. Then again, admittances in parallel can be added. Okay, that is again 1 by impedance. This is again RC minus JXC. So this is R minus JXL by R square plus XL square. R plus JXC by R square plus XC square. So this Y total is R by R square plus XL square, R by R square plus XC square, plus J if you take XC by R square plus XC square minus XL by R square plus XL square. Now again, if you observe, this is the net susceptance. This is the net susceptance you have to equate to 0. If you equate the net susceptance to 0, yes. Now if you equate the net susceptance, again at omega equal to omega naught, we know net susceptance is 0. If you do that, then we get, I'm directly writing, then we get this F naught is equal to 1 by 2 pi root LC, root of, okay, root of L by C minus RL square by L by C minus RC square. This is the third name. Now conclusions are dynamic impedance. Now this is important. Dynamic impedance. Dynamic impedance is also called Z dynamic. Here gate bit came, sir. Dynamic impedance, that is Z dynamic. Okay, dynamic impedance or Z dynamic. Okay, what is this? Now listen. It is the impedance offered It is the impedance offered by the it is the impedance offered by the network to the source. The impedance offered by the network to the source under resonance condition. Okay. It is the impedance offered by the network to the source under resonance condition. Okay, it is the impedance offered by the network to the source under resonance condition. Okay, dynamic impedance. It is the impedance offered by the network to the source under resonance condition. Now, sir, chalo, first for series RLC. Now, anyone tell me what is the dynamic impedance for series RLC? Because it is R plus JX net reactance is 0. Then for series RLC, Z dynamic is R only. Okay, Z dynamic is R only. Be it. For parallel RLC circuit, Z dynamic. See, for parallel RLC circuit, admittance is 1 by R. Net susceptance is 0. Impedance is again R only. Now for tank circuit, this is interesting. For tank circuit. Listen, sir, for tank circuit, what is the dynamic is asking. Now you see now. See, for tank circuit, you see this is the ideal tank, not ideal tank. This is called practical tank. Yes. For tank circuit, this is the admittance, sir. This is the this is the net admittance. But you know, under resonance, under resonance, net susceptance is 0. Then this y become what? R by R square plus XL square. Then what is Z dynamic? Admittance na? Admittance is R square plus XL square by R because reciprocal. Because under resonance net susceptance is 0, admittance is this. So impedance become ulta to this na. But what is RL square plus XL square L by C na? So if you substitute back, this is L by C, L by RC ohms. This is Z dynamic. So Z dynamic will be what now? L by RC ohms. This was the gate bit, sir. Z dynamic is L by RC ohms. Then, however, for ideal tank, now I am writing ideal tank. Chalo, for ideal tank circuit, everybody, for ideal tank circuit, what is Z dynamic? Now, if you go for ideal tank Z dynamic, yes, if you observe for ideal tank and Z dynamic, okay, na? Yes, in this case, if you observe that ideal tank and Z dynamic, okay, everybody observe now, ideal tank and Z dynamic. Okay, here's something interesting. Now, for ideal tank, yes, you see, admittance is this, but under resonance, net susceptance is 0. Net susceptance is 0 means admittance is 0. If admittance is 0, impedance is infinity. If admittance is 0, impedance becomes how much? Infinity. Yes, infinity ohms. It acts like open circuit. Open circuit OC. Open circuit OC. Open circuit OC. Okay, these are the important things. Such bits are asked. Okay, such bits are asked. Now see, there are interesting gate question. Now first gate question, everybody watch carefully. Okay. Under resonance, R naught is dash. We gave this circuit. Watch careful, sir. Very interesting, straightforward question. Under resonance, R naught is what? This is R naught. Okay, is observing R naught. This is, however, RLC. Options are R naught is equal to R. Option B, R naught less than R. Option C, R naught greater than R. Option D, R naught is infinity. You'll answer this question, everybody. See, under resonance, this R naught is how much he's asking. Equal to R, less than R, greater than R, or R naught is infinity. Yes, everybody see now. Everybody see. Now, if under resonance, what is R naught? But this is nothing but dynamic impedance, na, sir. According to the concept, any impedance offered under resonance is called dynamic impedance. That means this R naught is nothing but Z dynamic only. But what is Z dynamic of tank circuit? L by RC. That means this R naught is L by RC. Good. But sir, from this you cannot directly tell whether it is greater than or less than or equal to R. Now let us expand that. Now you see in this derivation of tank circuit, you see in this derivation of this tank circuit, there is an interesting relation we got here. That is R square plus XL square is L by C, na? That is R square plus XL square is L by C. So from tank circuit discussion, we got that R square plus XL square is L by C. Now if you take R square common here, 1 plus XL square omega square L square by again R square is equal to L by C. Yes or no? You will get this as L by C. Yes or no? But what is this quality factor of? Yeah, quality factor of this parallel branch. So from that, if you observe, this R square into 1 plus Q naught square is equal to L by C. So 1 R you bring here. If you bring 1 R here, this is L by RC. 1 R you bring here, that R into 1 plus Q naught square. So out of R square, 1 R you bring here, L by RC is R into 1 plus Q naught square. But what is this L by RC is dynamic impedance. That according to the question is R naught only. So R naught is R into 1 plus Q naught square. Yes, we got this. So clearly R naught is greater than R because quality factor is always positive and anything square is again positive. So it is always greater than R. So answer is R naught is greater than R. Greater than R. So many will say, sir, under resonance equal to resistance. So they will put option A. That is wrong. At the same time, so many will say, are parallel under resonance infinite impedance. No, infinite impedance is only for ideal tank. For practical tank, this R will be much greater than R. That is the meaning there. Okay, that is a very, very interesting conclusion. Now, another important question, sir. Another important question I'm giving. Okay. Yes, another important question I'm giving. Everybody. The network below. Okay, this is also gate question. The network below acts as dash filter. Okay, acts as dash filter. The network below acts as dash filter. This is VI, this is VO, this is R1, this is R2, this is L, and this is C. The network below acts as dash filter. Everyone please understand the question. Okay, the network below acts as dash filter. Okay, yes, please look into this. The network below acts as dash filter. Okay, options are low pass filter, high pass filter, okay, band pass filter, band stop filter, low pass filter, high pass filter, band pass filter, band stop. Yes, low pass filter, high pass filter, band pass, and band stop. Okay, na? Chalo, I'm giving the solution now. Everybody watch this solution now. Okay, now see this. Now filters are such circuits which operate for range of frequency and attenuate or stop certain range of frequencies. If it is allowing lower range of frequency, low pass filter, higher range of frequency, high pass filter, like that. Chalo, let us test by varying the frequency. Let us vary the frequency of supply VI. So this input signal is there, na, sir. Yes, let us vary the frequency of this input signal. Chalo, first at omega equal to 0. At omega equal to 0, you know, inductor acts like short, capacitor acts like open. Yes or no? Everybody see this circuit operates like this. At 0 frequency, inductor short, capacitor open. Okay, this will act like this. This is however R1, this is however R2. Let us say this is VI, let us say this is VO. Now voltage division rule. Output voltage is total voltage into same by sum. Okay, output voltage is total voltage into same by sum. Then voltage gain. Voltage gain is, yes, then voltage gain is, okay, this voltage gain is VO by VI. Okay, VO by VI, that is nothing but R2 by R1 plus R2. Okay, then at omega equal to infinity. At omega equal to infinity, now see sir, infinity frequency inductor open, capacitor short. Okay, inductor open, capacitor short. Inductor open, capacitor short. Now this is R1, this is R2. However, this is VI and this is VO. So this VO is VI into R2 by R1 plus R2. So here also voltage gain. Voltage gain means output voltage by input voltage. So if you take that ratio, this is again coming as R2 by R1 plus R2. Fantastic, sir. So at low frequency and high frequency, certain amount of output is coming. But now, sir, now tell me, can this circuit undergo resonance? This circuit can undergo resonance because both L and C are there together. And you see now, this part of segment alone is ideal tank. Na? This part of segment is like ideal tank. Actually, this circuit can undergo resonance as both L and C are interacting together. And moreover, this part becomes pure LC in parallel. That is ideal tank. This part alone is called ideal tank. Yes or no? This part alone is ideal tank. Now, so at omega equal to omega naught, which is 1 by root LC, because ideal tank resonance frequency is, sir, at ideal tank resonance frequency 1 by root LC, this ideal tank acts like what? Now see this, sir. See, the ideal tank under resonance dynamic impedance is infinity, it acts like open circuit. Ideal tank under resonance dynamic impedance is infinity, it acts like what? Open circuit. So now what is going to happen? Yes, then this is acting like open circuit. This is acting like open. This is R1, this is R2, but this dynamic impedance under for ideal tank under resonance is how much? Open circuit. Now when this is open circuit, output is zero, so gain is also zero. Output is zero, gain is zero. So if you plot frequency characteristics, that is gain versus frequency, gain versus frequency. Now at low frequency and at high frequency, at low frequency or high frequency, this is R2 by R1 plus R2. Okay, R2 by R1 plus R2. Okay, but what is happening now? But what is happening? Yes, this becomes something like this. This becomes something like this. This is becoming something like this. Okay, so this is omega naught. Okay, at low frequency or high frequency, this is something like this. Okay, na? At lower frequency or higher frequency, that is something like that exists, and at resonance frequency it is zero. So clearly, what filter, sir? It is this is clearly band stop filter, band stop filter, or band rejection filter. Okay, band rejection filter. So with this we give complete detail. Yes, with this we give complete detail of resonance. Sir. Resonance, everything I did, sir. All gate bits, all IS bits I did at one place. Okay, na? So we will take another 20 minutes to start introduction to magnetic circuits. Or shall we stop? Tell me your feedback. Shall we stop or shall we start magnetic circuits? Everybody give your feedback right here in question answer. Continue, stop, go on, start, sir, stop, enough, sir, stop, stop, continue, introduction, stop, stop, start. Are equal to your giving, start, stop. Okay, 20 minutes introduction I will give. Okay, na? Chalo. I will give 20 minutes introduction. Okay, na? Just 1 minute gap I am giving, and we'll take 20 minutes introduction to resonance and magnetic circuits, and we'll stop somewhere around 12:30, 12:40. Okay, just 1 minute gap. Yes, everybody. Just introduction I will give. Okay, na? Just introduction to magnetic circuits I will give. Okay, everybody. Resonance is one of the big chapter, but everything I gave, sir, everything I gave at one spot. You can check now. Not even a single bit I left, single topic I left. Okay, but expand based on this. Okay. So now this is another part of AC steady state called magnetic circuits. Magnetic circuits. Okay. Now see, charge at rest. Charge at rest is called what? Static electricity. Charge at rest produce only, okay, produce only electric field. Electric field. Okay. This is called electrostatic. Electrostatics. Okay, charge at rest produce only electric field, that is electrostatic. But charges in motion, okay, there is current electricity, okay, there is current electricity concepts, okay, current electricity produce both, okay, produce both electric and magnetic fields. Charge at rest produce only electric field, but charges in motion produce both electric and magnetic fields. Okay? Yes, charges in motion produce both electric and magnetic fields. In that, A, steady currents DC produce time invariant, okay, magnetic fields. Okay, then B, AC currents, okay, produce time varying magnetic fields. Okay, charges in motion, that is current, produce both electric and magnetic fields. In that steady current DC produce time invariant magnetic fields. AC currents produce time varying magnetic fields. Okay. Now to start this chapter, so that is why so far we neglected this effect of magnetism. Everybody see, so far we neglected the effect of magnetism. Okay. So far we neglected the effect of magnetism and we studied some. Okay. But now we will introduce. So now we will introduce the effect of. Yes, we'll introduce the effect of this magnetism and then we'll study. Now to start this chapter again, the first major notation we require is, yes, notation is Ampere right hand thumb rule. Okay, the first major notation I require. Okay, notation I require is, yes, Ampere right hand thumb rule. Okay, Ampere right hand thumb rule. Okay, so if I apply that Ampere right hand thumb rule, okay, yes, in a straight current carrying conductor, okay, in a straight current carrying conductor, if current direction is indicated by the thumb, then the closed fingers indicate the orientation of flux. The closed fingers indicate the orientation of flux. The closed fingers, okay, na? The closed fingers indicate the orientation of flux. The closed fingers indicate the orientation of flux. Okay, that is the meaning. Actually, these are vertical cylindrical lines, three-dimensional, which I'm not drawing here. But if current is indicated by thumb, closed fingers indicate the orientation of flux. Right hand only, sir, right hand only. If current is indicated by thumb, then closed fingers indicate the orientation of flux. Okay, yes, if current is indicated by the thumb, the closed fingers indicate the orientation of flux. Okay, and if you take vice versa, but if current is coiled like closed fingers, then thumb is flux. Ulta. So if current is straight in a conductor, thumb is current and closed fingers are flux. But if current is coiled like closed fingers, then thumb is flux. Vice versa, sorry. Current is thumb, flux is closed fingers. If current is closed fingers, flux is thumb, like that. Okay. Now another important notation, sir. Here you see current is entering the conductor. So we call this as cross notation. We call this as what? Cross notation. Now if I look the top view here, current is coming out from this cross section of current. That is called dot notation. Dot concept. Okay, dot. So in a conductor cross means current is entering the cross section area of the conductor. In a conductor dot means current is coming out of the cross section of conductor. That is the meaning of cross and dot. That is the meaning of cross and dot. Okay, that is the meaning of cross. Okay, so that is the first thing. Then let us understand permanent magnets versus electromagnet. Permanent magnet. Okay, though this chapter is not about permanent magnet, but you know permanent magnets have high retentivity. High retentivity. That means they will retain magnetism for a long time, and they are hard magnetic materials. Hard magnetic materials. Hard magnetic materials like alnicos, okay, samarium cobalt, etc. Okay, this samarium cobalt is our toy magnets, black color one, that is the earth material, sir. So like a bar magnet, if I take like permanent magnet, okay, this is north pole, south pole. What is the notation? Notation is flux leaves north pole externally, enters south pole externally. Okay, internally they go from south to north, externally north to south, internally south to north, externally north to south. Flux leaves, here flux enters. Externally flux leaves north pole, internally flux goes from south to north, externally north to south. But how many flux lines leave? That many flux lines come back. Then what about electromagnet? What about electromagnet? What about electromagnet? They have low retentivity. Low retentivity. They have low retentivity. They are soft magnetic materials. Okay. Yes, they are low retentivity, soft magnetic materials like silicon steel, soft iron, ferrites, okay, ferrite materials, etc. Okay, ferrite material, etc. Okay, now what is the meaning of low retentivity? You give current, they are magnets. You remove current, they are not magnets. Now your notation. Now this notation is, yes, I am taking 2 iron rods. Okay, I am taking 2 iron rods, solid iron rods, and I am having a copper winding around them. See the difference? In the first case, I have copper winding like this. In the second case, I have like this. Observe the difference, how I am winding them. And I am allowing current to go like this. Now this is surface X, this is surface Y. Here also surface X, surface Y. So which pole is what? Which surface is what pole? Okay, apply right hand thumb rule, everyone. Yes, apply right hand thumb rule, everyone. See, in the first case, you see current is going. See, in the first case, you see current is going above the rod from our view. In the second case, current is coming from below to above, or below to above. So if you apply right hand thumb rule, now closed fingers is current, sir. Here fingers of right hand thumb will go, closed fingers of right hand will go above the rod. So thumb is showing left side. So clearly thumb is showing left side. So flux is left side. So clearly flux is left side means, yes, this X become north pole, Y becomes south pole. But you see in the down, see the current is going the other way. That means the closed fingers right hand thumb rule, the closed fingers of right hand is going from below to above. It is going from below to above. That is the direction of current. Below to above the rod. Below rod to above the rod. So thumb is showing right side now. Thumb is showing right side means flux is leaving Y and flux is entering X. So flux is leaving Y means flux is leaving Y. This is north pole and this is south pole. That is the meaning. Okay, that is the meaning. Simple meaning of right hand thumb rule. Okay, simple meaning. Another notation. Suppose there is a conductor cross and current I give, and here I am giving another conductor dot, and now I want the orientation of flux. Okay, now this flux is oriented around it. Flux is oriented around it. Which direction I want? Here also flux is oriented around it. Flux is oriented around it. Like our transmission lines, you are seeing the cross section area. Now here you see cross means current is entering the conductor. Cross means current is entering the conductor. That means thumb is entering the conductor. Thumb is entering. Here current is straight now, so thumb is straight. Current is straight, thumb is straight. In the previous model, you see current is coiled. Closed fingers are current. But here you see cross means current is entering the conductor, so thumb is into the board, so clockwise. If thumb is going inside the board, all these closed fingers is going right side clockwise, na? Yes, this is like a clockwise. Yes, this is clockwise oriented, so flux is clockwise orientation. But here you see dot means current is coming out of this conductor. Dot means current is coming out of the conductor. If current is coming out of the conductor means thumb is showing upward. So closed fingers show left side, anti-clock. So closed fingers are showing anti-clock. So flux is anti-clockwise. Anti-clockwise. Okay, na? Anti-clockwise. Okay, na? Then again if you observe. So then again if you observe. Okay, here there is a circular ring. Okay, where current is going this way. Here also there is a circular ring where current is going this way. Here there is a circular ring where current is going right side. Here also there is a circular ring where current is going left side. Now this is surface X and this is surface Y. So X is dash pole, here Y is dash pole. X is dash pole, Y is dash. Now if you show here, see the circular ring closed fingers are current. The circular ring closed fingers are current. If current is going this way, the thumb is hitting the board. You see now, the current direction is closed fingers direction, sir. If current direction clock is closed fingers, thumb is going down, means thumb is hitting the surface. Thumb is hitting the surface means X surface is what pole? Yes, south pole. Okay, south pole. But here current is going anti-clock, means closed fingers are anti-clock. Thumb is going up then. Thumb is going up means current flux is leaving the surface. So Y is north pole because flux is leaving the surface. North pole. North. Okay. These are the notations to start with. Okay. Tomorrow we will start everything. Okay. Tomorrow we will start everything. Okay. Chalo now, sir. Relaxed, very relaxed. Doubts will go. Tomorrow we will complete this magnetic circuits and then we will start transients also. But you have to cooperate, sir. Please. Chalo. Now everybody. Yes. Pawan, what is your doubt? Anyone doubt? Pawan doubt? Okay. Vinita doubt?
Sir, in the list of dual elements.
In the list of dual element. Tell me what is your doubt. I can understand. Tell me what is your doubt.
Sir, their switch in series getting open means switch in parallel getting closed now, sir.
If switch is ulta, if switch is getting closed in series, switch is opening in parallel, like that also. See, both ways you have to see. Like for example, switch is getting opened means switch is parallel getting closed. Yeah. Here I should write, or here I will write ulta. Anyone I will correct. Very good, sir. You gave me correction. Please see everybody. One student gave me correction. This is a correction. Fantastic, given by one student. Very good. You are reading everything. Your name? What I told? What you told? Your name?
Vinita, sir.
Vinita. See everybody. Vinita gave a correction here. See. If switch in series is getting closed, its dual will be switch in parallel getting opened or vice versa. If switch in series getting opened, switch in parallel getting closed. So please, there is a correction here, everybody. Please go to the last previous slide and there you put a mark or write somewhere in your notes that there is a correction. Switch closing is dual to switch opening. Series, however, become parallel. Okay? Yes, Vinita. Thank you. Anything else?
Nothing, sir. That's it.
Yes. Sangeeta, what is your doubt? Sangeeta, what is your doubt? Sangeeta, can you listen? Tell me what is your doubt? Okay. Pranjali?
Sir, no doubt, sir.
Okay. Pranjali, tell me your doubt.
Sir, can you repeat that frequency of energy oscillation between L and C under resonance is 2F naught?
I will explain. Okay, see in series RLC, first you understood the phasor diagram, na?
Yes, sir.
Now if you project the phasor, these are the waveforms, na?
Yes, sir.
Now you see, I am taking one cycle. One cycle of supply means 360 degrees.
Yes, sir.
But already this is operating at what frequency? Resonance frequency, na?
Yes, sir.
Because this is the phasor diagram under resonance only we are talking. So this one cycle of supply, which is 360 degrees, is operating at resonance frequency already.
Yes, sir.
Now for inductor, always see the state variable inductor current, and for capacitor, see the state variable capacitor voltage. So at 0 degrees, current is 0. So inductor energy is 0, but half CV square is maximum. Yes or no? and 90 degrees, current is maximum. So inductor energy is maximum, but capacitor energy is 0. So that
Yes,
means
sir.
from 0 to 90 degrees, capacitor is giving back to inductor. Capacitor stored energy from static form is given to magnetic form.
Yes.
But when they would have got this energy, they would have got this energy during tuning process or during turn on process. Transient is there now. During tuning process or turn on process, that time they would have got this energy.
Okay.
Then again from 90 to 180, see at 180 what is happening? Current is 0, so half Li square is 0, but half CV square is maximum.
Yes, sir.
So now you see capacitor to inductor and inductor back to capacitor is like one cycle now,
Yes, sir. Okay.
which is happening in the half cycle of supply. Again capacitor to inductor, inductor to capacitor is another cycle.
Okay, sir.
So for one cycle of supply, capacitor to inductor, inductor to capacitor, again capacitor to inductor, inductor to capacitor. So 2 cycles of energy oscillations.
Okay, sir. Understood.
Very good, very good.
Thank you, sir.
Anything else? Anything else, Pranjali?
No, sir. Clear.
Good. Imtiaz?
Good afternoon, sir.
Yes, Imtiaz, tell me, Imtiaz.
Sir, in the resonance of the wave, the point is that acceptor circuit is the
Acceptor circuit. Tell me what you get out.
Sir, what do you mean of acceptor means is the current acceptor?
See, like in your old radio, these concepts are there. Suppose in your old radio, you are tuning the gong. Actually, the gong is a variable capacitor.
Okay.
In old radios, when you are tuning the gong, there is a variable capacitor. So, what is the meaning? You are varying the natural frequency of the circuit by varying the capacitor, because resonance frequency is 1 by root LC, na, omega naught.
Yes, sir.
So, as you are varying the variable capacitor, you are varying the natural frequency. And when radio station frequency and your circuit frequency are matching, both are said to be under resonance, then this radio circuit will exhibit low impedance. Low impedance means it will accept the current signal, that is a wave, which is our signal coming from radio station.
Okay, sir. Means
So
it's
that's why we call this is acceptor circuit.
okay, sir. I got it.
Okay?
One more, sir.
Tell me.
Sir, in yesterday class, we are discussing that problem. It means after a special case, see, I asked that doubt external, sir.
Tell me, what is your doubt?
Sir, in that, I conclude that what we said in maximum power transfer theorem,
Yes.
the load side is the voltage is the Vs by 2, means 50% of the source voltage.
Yes, correct. Load side magnitudes are however equal. So magnitude of supply voltage will be 50%.
Means it's applicable for both DC and AC, no, sir.
Absolutely true.
Is that right, sir?
Yes, it's applicable both AC and DC.
Okay, sir. Sir, one more, sir.
Ah,
Could you draw that circuit, sir? I have drawn in that. Means
which circuit you are talking?
other circuit, sir. In general circuit. Just like that.
In general circuit means both resistance and impedance are variable, right?
No, sir. No. One is parallel, sir. R and L are in parallel.
Okay. One is R and L in parallel, the other is?
Both are, the load is parallel, R source is in parallel. Both load and source.
R and L are parallel. You are talking like this?
No, sir. Load and source are in parallel, sir. In source,
Okay.
R and L are in series.
Okay. Tell me now what is the doubt?
Load is in parallel.
We can say it is either parallel or series. This correction is called either or. Current is also equal, voltage is also equal. That is why in Hayton Kemmerly such controversies he will say either or. But if third branch comes, then they are parallel.
Sir, the source is current source.
Okay, if source is current source,
Yes, sir.
then what is the doubt?
Sir, the maximum power transfer at the load side is P is equal to IL square into RL to ZL, sir. I consider
Here current, see, here we cannot do any tuning because current is always constant.
Yes, sir.
Because current source will always drive constant current. So higher the R value, higher the power.
No, sir. One more draw that load side, sir. This is not load, this is source. RS and LS.
Okay, you are taking current source,
Sir, same circuit. One more
same.
parallel path, sir.
See, same circuit, one more parallel. What parallel? Which is in parallel?
That is a load, sir. It's not given. That's a load.
Okay.
Box.
Okay.
It's asking the maximum power. at that load.
And what you do, my suggestion is what you do, first convert this current source in parallel with impedance to voltage source in series with impedance. Then our controversies are gone.
Yes, sir, but considering that point means PL equal to IL square into generally RL or ZL, sir. That's one point.
RL, real power, always real power.
Sir, why not ZL, sir?
See, we are all maximizing the utilizable part of energy. We will never maximize the stored energy. Consumer finally is utilizing which energy? In your house also, we are paying bill for which energy? Kilowatt hour, na?
Yes, sir, real power.
Utilizable part is maximization. What you will do maximization with the field energy, then reactive power will increase and power factor will go down. Again, it is underutilization only, na?
Okay, it means whenever he has only in the form of the IL square into RL.
Yes.
Okay, sir.
Okay.
Thought that's okay, sir. I got it.
Good. Understood. Good.
Thank you so much.
Right. And Navdeep, what is your doubt?
In parallel resonance condition, sir, you said that
Tell me.
that L and C will be open circuit, sir.
Together they act like open circuit. Now what is your doubt?
Then how current will flow, sir? You are
Current
saying
will
that
flow.
it will.
Listen. That is what we are arguing, na? See now, carefully listen. See, under parallel circuit, L and C branch is open, but R is still there, na?
Yes, sir.
So that means this source current will flow. This source current will flow only here in the resistor. But this L and C together, they will be allowing current by oscillating the energy from magnetic to static, static to magnetic, magnetic to static, static to magnetic. But when they would have got this energy, during turn on process or transient or while tuning the circuit to resonance frequency.
Sir, that energy that's stored at that time, that is oscillating, and due to that current is magnified. Sir.
That energy, whatever they store initially during tuning process or during transient, will be amplified to Q times.
Okay, sir.
And that energy, because of that magnetic and static keep exchanging and currents are flowing. But source current is flowing only through resistor.
Okay, sir.
Okay?
Okay, sir.
Okay, right. So everybody tomorrow 7 o'clock again. Please come tomorrow 7 o'clock, everybody. Okay?